In this domain, we're going to be looking at telecommunications and networking. We're going to be reviewing the TCP/IP suite. We're going to look at cabling and data transmission types. We'll be looking at different technologies relative to distance. We'll be looking at the LAN, that's a local area network, the personal area network, PAN. There's one in the middle called MAN, Metropolitan Area Network. And then we'll look at WAN, Wide Area Networks. Then we'll be looking at network devices and services, telecom protocols and devices, remote access methods and technologies, some fault tolerance mechanisms, and then finally we'll be looking at some attacks on telecommunications and networking.
Now we're going to go over the OSI model, which is a core concept of networking. We're going to look at actual network types, which means how computers actually communicate to each other over some type of channel, whether it be Ethernet and copper, or it's wireless and radio frequencies. And then we'll look at physical topologies, which is how devices and computers are actually physically put together on a network. So the OSI model, a lot of people have heard of it. They memorize like layer 3, that's networking, or they'll memorize a data link, that's layer 2. But I have found that a lot of people actually don't know really what the OSI model is, what it's for. And I think it's pretty important because not only is it the network stack that your computer uses for communication over any type of network, but this is where a lot of attacks take place. There could be attacks at different levels, and you wouldn't know what type of safeguard to put in place. So we looked at the physical topology. Now we're going to look at the media access technology that works at the data link layer, and that will be token ring and other token passing types of protocols, Ethernet, token ring, those types of protocols. So when I talk about the MAC level, the media access control level, it's not just that it's doing framing, and it's not just that it's doing encoding of the frame that's getting ready to be turned into electricity. What's also going on is how the computer is going to deal with any type of errors, if you have transmission errors, or to try to ensure that messages or frames don't collide on the network itself. So there's different types of technologies built in to determine how computers are going to talk to each other, how they're going to deal with errors, how they're going to deal with any type of collisions that take place. So we're going to look at what's called CSMA CD, CSMA CA, token ring, token passing, polling. These are the types of things that help computers basically architect how they're going to communicate to each other. And remember that we have the physical, and right now we're talking about the data link layer. Now I said there's actually 2 sublayers. What are the 2 sublayers at the data link layer? Well, there's the logical link control, which is 802.2, and then there's the 802 dot fill in the blank. If it's Ethernet, it's 802.3. If it's wireless, it's 802.11. So we're talking about basically the bottom part of the data link layer. So one of the goals is to ensure that there's not corruption of the data as it goes over the wire. And one of the things that takes place is called collisions. So if you put data on the line, I put data on the line, our our frames can collide, and what happens is it corrupts the data most likely, and we're going to have to resend our data, so that causes performance issues. So one of the components of trying to ensure that communication takes place smoothly is to ensure that collisions don't happen. Now, when you're architecting a network, one of the things that you need to look at are your collision domains. And basically, if you have a specific subnet, if you have a segment of the network, the more nodes, the more computers that you put on that section, the more collisions that are going to take place, because there's more systems that have to communicate. And this is it's called contention. Contention means that different systems are competing for the same resource. So it'll be contention over that actual network link. All of us we only have one UTP line to communicate over. So the more that you put on that line, the more collisions that are going to take place, which reduces the performance of your network. And again, the system competing over that line, UTP or STP or fiber, they're all competing over this one communication channel. And so it's called chatty. And it has more collisions than any of the other LAN type of protocols that we'll look at. But the reason it won is because of the speed, because we're up to like gigabytes throughput speeds. Now, another approach to dealing with how systems communicate and how we try to ensure that collisions don't take place is called token passing. And token passing, we have different technologies. There's token ring, there's ARPANET, which did not win any war, it's dead, we don't use that anymore, Fddi. These are technologies that use token passing. And the architecture that's set up, the physical topology, is a star. Even though it's called a ring, the ring is at the data link layer. The physical topology is a star. So this central device is called the MAU, the Multi-Station Access Unit, and all the other systems are connected to it. Now, where the ring comes in is that there's a logical ring within the central device. And so there's a token, and what the token is, it's actually an empty frame. And no computer can put any data on the line unless it has a token. So when it goes, the frame, the token will go up to this system. If it has nothing to say, the token goes back empty onto the line. It goes up to this system. Now this system has data to put on the network. So what it does is it puts its data on, it changes that token to the address of where it needs to go. Then the data is put on the line, it goes to the destination. The destination system will make a copy of the data. It doesn't actually take it off the line and delete it. It copies the data. It basically switches a bit within the token that says now it's free. Or that bit switch says, I got it. So again, the sender will basically change the token with a bit saying it's going somewhere and it's got some data. It goes around the line. The receiver changes a bit on the token saying, I got it. But that data goes all the way back to who sent it, and then it will take it off the line. So you see how, since all systems can't communicate at the same time, yeah, there's no collisions. That's great. But it's slow. If only one system can communicate at the time, it's very slow throughput. But it's not just token ring that uses token passing technology. Token ring is one LAN protocol, and its standard is the 802.5. So again, some people get confused about the physical ring versus the logical ring. There's definitely a difference. A logical ring will happen within the device, and sometimes it's called a collapsed ring, and that's where the ring actually is, because it'll go out and say, do you need anything to say? No. Do you need anything to say? No. Do you need anything to say? So it's going in this circular motion. But usually the actual physical topology would be a star, because it has a central device that's actually keeping track of that token, and to make sure that there's always a token, make sure there's not two tokens. So I said that other technologies use token passing. And we're going to look at Fddi a little bit more when we get into the MAN technologies. Fddi has been used as a backbone technology in LAN environments for a long time, It's not used as much anymore because Ethernet has actually hit the same gigabyte throughput, the Fddi. But Fddi is used as a backbone within a LAN, or it can go over a MAN, Metropolitan Area Network. And it does the same thing. It has a token. It actually has 2 tokens to allow 2 computers to communicate. And then, so there's Fddi, which goes over, that carries data. And then there's Fddi 2, version 2, which allows to move other types of data, voice data, video data. And as I said, ArcNet is another technology that uses token passing, but it's done. We don't use it anymore. So the last data link communication method we'll look at is called polling. Polling isn't as popular or used as much as the other ones that we talked about. In mainframes, that's where polling is usually used. And what this means is that you have a primary system that polls, asks secondary systems, do you have anything to say? Then it goes to another one, do you have anything to say? Do you have anything to say? So this primary system is controlling when the secondary systems can actually put data online or communicate. Again, this isn't used like necessarily in our network LAN environments. It would be more of communication with a mainframe, or if you had more than one mainframe that needs to communicate. And that type of polling is built on protocols that use SDLC, HDLC, which we're actually going to get a little bit deeper into in this domain.
So the business of networking and telecom has to do with getting data from one point to another. To do this, we use cabling very often. We'll look at cabling types such as coax, twisted pair, and fiber optics. We'll also be looking at transmission types, analog and digital. There are advantages and disadvantages of each of these technologies, and we'll be exploring those. The first type of cable we'll be looking at is coax. Coax is used in radio frequency transmissions, and it has a center conductor that actually carries the data signal itself. That center conductor then is surrounded by an entire shield that is grounded. As electrons flow through the center conductor, the electron flow produces a magnetic field around the cable itself. This propagation of the magnetic field takes energy away from the data signal and degrades the data signal. So now we wrap a metal shield around that center conductor to contain the magnetic field, and this allows the signal to propagate greater distances. Two main cabling types are ThinNet, which is 10^2, which was used in the old ThinNet networks, ran about 185 meters and required terminators at the endpoints. Another type of coax cable that was used commonly is ThickNet 10^5. It's about the consistency of a frozen garden hose, and it ran about 500 meters. Coax cabling was typically used for one-way transmission. These days, more and more, we see these being used in bidirectional or two-way networks. A two-way network requires a transmitter and a receiver at each endpoint. The next cabling type we'll be looking at is twisted pair. There are two main types of twisted pair, shielded twisted pair and unshielded twisted pair. The shielded twisted pair uses 8 wires. The wires are twisted in pairs, one of them carrying data signal. The other is a ground wire that gets twisted around the data carrying wire. So I actually have 4 pairs of wires within a cable. Now inside that cable, in addition to those 4 wires or those 4 pairs, is a foil shielding that gets wrapped around those 4 pairs of wires. This was called shielded twisted pair. Now, shielded twisted pair didn't really help a lot. The specification for STP ran 101 meters, whereas unshielded twisted pair was good for 100 meters. So you got about an extra meter. It was a great deal of effort trying to terminate STP cabling. The unshielded twisted pair, or UTP, is by far the most prevalently used. It is also the least secure. Because the magnetic field is able to propagate outside the data carrying wire, it's much easier to pick up crosstalk, electromagnetic interference, radio frequency interference, and actually is subject to emanations attacks. In other words, I can detect the flow of data bits just from picking up the magnetic field that is propagated outside the UTP cable. So to summarize, we've looked at 2 types of coax, 10^2 called ThinNet, 10^5 called ThickNet. 10^T is unshielded twisted pair, was good for 10 megabits. 100^TX was good for 100 megabits, and 1000^T is called gigabit Ethernet. The next type of cabling we'll be looking at is fiber optic cables. Fiber is expensive, but it has the greatest performance. It uses photons instead of electron flow to carry the data signal. It uses glass fibers to carry those photons. So it has higher speed, less attenuation, and because it uses photons and not electrons, photons don't emit those magnetic fields. And as a result, emanation security is substantially better with fiber optics. Fiber optics are more expensive and more difficult to work with. With fiber optics, we're going to now look at the way that the photons actually flow through the fiber optic cable itself. In the diagram you see the step index multimode fiber. This is where you have a solid glass fiber, sometimes plastic, usually glass, but it has a cladding around it that has optical characteristics very different from the center conductor. This is called a step index function. The index they're talking about is called the index of refraction. What happens when we put one type of glass around a different type of glass and we have a great difference in their indexes of refraction is it creates a mirror effect between the fiber that is carrying the photons and the cladding, and it creates a complete reflection as you see in the diagram. In the diagram on the left, down at the bottom, we see the graded index. Now this is where we're using a fiber that has a graded index of refraction through the diameter of the fiber itself. And you'll see it doesn't have the sharp angles. The reflection actually occurs over time. So it creates a more sinusoidal wave. Next, we're going to be looking at some of the negative aspects, some of the detriments to cabling as far as carrying data signals. The first issue we'll be talking about is attenuation. Attenuation is the degradation of the signal as it travels over distance. The longer the distance, the more attenuation there is. So a very strong signal, very square, binary 1 bit on your cable at transmission point begins to look like a rounded hump, and it doesn't have the same amplitude over distance. So this is resistance, it's capacitance, it's inductance, and it basically degrades the signal. In other words, the receiver can't recognize whether or not this is really a 1 or this might just be some noise or interference on the wire. And as a result, your data begins to get corrupted. Another negative aspect to cabling is crosstalk. Crosstalk is where we have generally parallel runs of wires, cables. And remember how I described the electron flow down the center of the cable and how it propagates a magnetic field. Even with coax, there's a magnetic field of some value around the coax cable itself. Well, if I have parallel wires running side by side, the magnetic field produced by one cable induces electron flow in the adjacent cable. This electron flow in the adjacent cable is interference, and it's actually going to degrade the quality of the signal in that adjacent cable. So again, it causes data corruption, it causes attenuation, and this is crosstalk from parallel cable runs. Again, the most susceptible to this is the unshielded twisted pair, the UTP, because it only has a wire wrapped around the data signal, and that doesn't provide a very cohesive, consistent shielding. Now we'll be looking at transmission types. Two main types, of course, are analog transmission and digital transmission. Analog transmissions use a sinusoidal wave, such as a radio frequency wave. It uses a carrier signal, generally at a single frequency that is the norm or the standard, and then they vary either the amplitude or the frequency to encode data bits into the signal. Amplitude modulation: as I increase the amplitude above the carrier signal, this might represent a 1 bit. If I decrease the amplitude from the carrier signal, this might represent a 0 bit. So the carrier signal is the standard, and then I will vary above that or below that standard to encode 1s or 0s into the analog signal. Another modulation type is called frequency modulation, FM, and this is where instead of having a frequency or a sine wave that is this long, if I increase the frequency, making the wave shorter, this might represent a 1 bit. If I increase the wavelength, decreasing the frequency, this might represent a 0 bit. So analog transmission is used in radio frequency transmissions, high frequency, and we use either amplitude modulation, frequency modulation. And newer technologies use also something called phase shift keying. We'll be talking about that a little bit more when we get into the wireless arena. The other transmission type is digital transmissions. With digital transmissions, I don't vary the voltage over a smooth pattern like a sine wave. What I do is I have either the existence of a signal or the absence of a signal. It's either a 1 or it's a 0, and there's nothing in between. This is a digital transmission media. With digital transmissions, I have two main types, synchronous and asynchronous transmission types. Again, this has to do with what's called modulation and encoding. This is the way I take those binary signals or digital signals and I encode data into those signals. So with synchronous transmission, synchronous meaning clock, synchronous transmissions are clocked. In other words, the sender and the receiver compare their clocks prior to. With asynchronous transmissions, we don't have that synchronization of clocks. So I have to tell the other guy, the receiver, I'm about to start talking. So I have to send him a start bit. The start bit says, following are going to be 8 bits of data. And after I send the 8 bits, I now have to tell them I've now stop jacketing of the Ethernet cabling that caused all these deaths. So anytime we're running cables in this plenum area, and by the way, that drop-down space between the true ceiling and the drop-down ceiling is called plenum. There's also plenum area potentially in a raised floor. Airspace above the true floor is called a plenum area as well. Anytime we're running cabling in these plenum areas, we have to run a cable that uses a jacketing using fluoropolymers. The fluoropolymers burn at a substantially higher temperature and emit less toxic fumes. They're still toxic, but at the point that we get that high temperature, we will now know this fire is happening and people will be evacuating the room. So again, anytime you're running cabling in these plenum areas, the drop-down ceilings or raised floors, you have to use plenum-rated cabling. Now the downside of running plenum cabling is it's about 3 times the cost of the standard jacketing. Standard jacketing, of course, is using the polyvinyl chloride, the PVC jacketing. Next, we're going to be looking at different transmissions. Now, a moment ago, we talked about multicast. Multicast transmissions are defined by a protocol called Internet Group Management Protocol, or Icmp. And again, this is where the recipient will register for a particular data feed, will bind a Class D IP address to their network interface card, will picture of the intranet. That's my trusted environment bounded by firewalls. And there's that public scary thing out there called the internet. An extranet would be a network that I connect to that is remote to my corporate network environment. In other words, I might actually have to run over public wires like the internet to connect to this other network, the extranet. Generally, when I do this, I will secure my data transmissions over those public wires by the use of VPNs, or virtual private networks. These VPNs encrypt all data flow from my intranet network to their extranet network. Here we're going to look at electronic data interchange. Now, EDI is a way that businesses communicate amongst themselves. In the old days, these were actually programs, custom programs that were written so that a manufacturer might be able to communicate his inventory information to the suppliers of that inventory. This was commonly used in what they call just-in-time inventory control, JIT, inventory control. So the manufacturer signs a deal with a vendor and says, I promise I'll buy all of my widgets from you as long as you see to it that my inventory of widgets never exceeds 200 but never drops below 100. So you monitor my widget inventory and you deliver to me a new supply of widgets just in time. This way I don't have to spend too much money on inventory on the shelf, but I never have to worry that I'm going to run out of inventory. This is a classic example of an EDI application. So again, this was a custom application written between suppliers and the manufacturing facilities. Primarily was used for inventory control. Today we do this much more easily than we ever did before with tools such as XML. It's really easy to build an XML website that is highly secure. Only the vendors are allowed to access this data. And I'll even run the data stream between me and the supplier over the internet through an encrypted channel. So I'll build a VPN from the supplier to the manufacturer. I'll build a custom website that provides them access to only one thing, my widget inventory, so that they can now monitor my inventory and deliver me inventory just in time.
Now we're going to go through different networking devices. And I talked about them when we were going through the OSI model, but now we're going to look at the actual functionality of the different devices themselves that are common on our networks. So a repeater, what layer did I say the repeater actually works at? That would be layer 1. We're talking about the OSI model, layer 1. And what happens at layer 1 is when the bits come down and they're put into some type of electricity. And so over like a copper wire, it's electrons that are moving back and forth. So at a repeater is not going to read any header information, it's not going to read any trailer information, it doesn't have any intelligence. All it does is it takes that, the transmission, and it amplifies it, which means it gives it more juice, you know, and then sends it on. And what I mean by gives it more juice is that when you have the, let's say, you know, let's say it's a copper wire, that's UTP, and you have these electrons that are going through the copper wire, what will happen is attenuation, which means the actual signal will start to degrade. So to be able to extend your network, you'll put repeaters there that will amplify the signal so it can get to its destination and be understood or be intact and not at a level of attenuation where the other computer can't understand it. So the repeater works at the physical layer. All it does is amplifies signals, and there's no decision making that it carries out. Now a hub is really a repeater. It just has more connections. Another name for a hub is a concentrator. And so a hub is where you have all of your computers or your devices connected to one thing, but this one thing has no intelligence. It's working at the physical layer also, and so it can't make a decision. It doesn't know when data comes in one port, what other port it needs to go out. So it actually just sends it out all ports. So when data comes in one port, it just sends that data to all the connections to it. Again, because it's working at the physical layer, which means it can't read any header information, which is instructions that will tell the devices where things need to go. Now, a bridge is something that does not just work at the physical layer, it works at the data link layer. And it makes decisions on what port some type of data has to go to. So let's say that you have a bridge, you have a computer connected to one port, then it needs to go to this system over here. Well, the bridge will know by its MAC address which port to send it out. The bridge has a responsibility of really understanding on this port, port 1, these systems live there. Port 2, these systems live there. Port 3, these systems. And that's how it knows when it gets a packet or a frame, which port it needs to go out. Now, I said that it's making its decisions on the MAC address. And in this domain, we covered IP versus MAC address earlier. But remember that the MAC address is a physical address. Your computer, the network stack, the IP address is at the network layer. A bridge works at the data link layer. It doesn't understand what's up here. So the bridge only understands the hardware address, and it makes decisions, forwarding decisions. And we say it's forwarding, where a router will route the data. Now, different bridges, the software in them, you can actually you can manually type out what systems are connected to what ports. Other bridges will basically come up empty within their actual forwarding table. They won't necessarily have all the systems. And what the bridge does is it sends out probes through its different ports and listens to what traffic actually comes back. And it'll start building its table of where things live on what port. And as an administrator, you set up forwarding tables, and you can do filtering, but based only on the MAC address, filtering based on that hardware address, not IP, because it's not working at the network layer. Now, we have bridges that can work at a higher level today in our environment. Most of the time we use the switches, which we'll talk about, but for the exam, the bridge works at the data link layer, and really that is the main place that it works. It can have different types of products, can have other functionalities, but the main place that it works is working with that MAC address at the data link layer. So what our networking environments have moved to is switches. We don't really use as much bridges anymore. We use switches, which the core of it works at the data link layer, where it's making decisions on the MAC address of which port to send it out. Now, the reason that we've moved from bridges to switches is that bridges will make its decision on which port to send it out in software. And the switches actually make its decision in hardware, which is always faster. So switches are much faster than bridges. And we're going to talk about another type of thing that switches bring to the network that bridges and other types of devices don't. And that's called a VLAN. So a switch, you're able to actually set up virtual LANs, a virtual network. And who cares? What's so great about that? Well, before we had actual VLAN capability, the network segments were set up based on where they were physically located. So all of the systems that were physically, they're on the first floor and they're over in this side of the building, then that's one segment. But not necessarily, those different systems may need access to different resources. What happens in a VLAN is you can actually connect, you have a virtual LAN, you could think of it as a container, and a system on the first floor, a system on the second floor, a system in another building can all be put in this container, and then you can assign resources. Maybe these need to communicate to the HR database. Maybe it needs to communicate to a specific WAN link. Where we were physically had constraints of setting up our network. Now VLANs allow us to logically segment our VLAN based on what those systems actually need access to. Now another benefit of a VLAN is that you can apply different security policies to it. So VLAN 1 can have a security policy which indicates what resources the devices in that VLAN can access. It will, what operations it can carry out. And then VLAN 2 can have a totally different security policy where those devices can access another set of resources and they can carry out other operations. So it allows us to not only virtually be able to create our network segments, we can then actually control the security on them based on the needs of what they need to access, what they should not be accessing, and what type of permissions and access control we want to allow them. So again, it's switches, and some routers provide VLAN, but in the exam, we kind of learn it face on exactly. We'll talk about firewalls. There's different types of firewalls, even though in the industry, the firewall vendors mix those different technologies up. Even within switches and routers and what we're talking about, different products will combine them. But for the exam, you need to know that really the basic definition of the functionality that these devices provide. So the switch will provide a VLAN, and basically a switch is like a multi-port bridge or a hub, and so it has these different ports, and each port a lot of times is its own VLAN. So VLAN 1 is connected to port 1, VLAN 2 is connected to port 2. So when a system needs to communicate within its VLAN, that information actually tagged. It's tagged saying this is within VLAN 1, so it will go to the systems within its VLAN. Now, one issue that I don't know that the exam will actually get into, I don't know if it gets this deep, but VLANs don't necessarily provide the best security. Now they do provide security in that you're doing the segmentation and you're able to apply different security policies, but there is ways that hackers can hop VLANs, and there's been some exploits that's been carried out to do that. So if you think about it, when we're talking about software's usually has some type of flaws, some way of busting out of the constraint. So there is VLAN hopping, which can be done where some systems can communicate to other systems that they're not supposed to. But again, I'm not sure that the CISSP is actually going to get into the VLAN hopping, but it's important that you know, especially if you're administrating this type of environment, that you understand VLAN hopping and how to prevent it. Now, sniffers. A sniffer is something that sniffs the wire. It basically has a NIC, a network interface card, that's in promiscuous mode, which means that it can understand or it picks up all the data, all the frames that are going back and forth. Because our NICs will only look for our MAC address, broadcast frames, and if we're participating in a multicast, that's what our NIC driver, you will have configurations in your network settings, and your NIC driver will enforce those settings. So where our NIC driver usually looks for, specific packets or frames that are only supposed to come to our computer, a sniffer will look at all of it, will process all of them. And the sniffers are dangerous because you can actually get some sensitive data. But with VLANs, what's important to know is that a sniffer can't actually sniff all the different VLANs. If a hacker puts a sniffer on let's say a LAN that's using just Ethernet, and it's using bridges or routers, since they're all communicating, they're contending for that one line, the sniffer can actually pick up all the data. But on a VLAN, they're actual separate communications. It's logical, but they're separate networks. And when we look, we went through IDS, intrusion detection systems, in domain 2, and we talked about a difficulty of an IDS actually in a switched environment. And the difficulty of IDS in a switched environment means that really an IDS, a network IDS, is a sniffer. It's just, it has to pick up all of the traffic. Well, if the traffic is going through individual, their own individual communication links, then a sniffer can't go across all of them. So with IDS, what we have to do is we set up, we basically set up a mirrored port which has all the data that's actually moving through. There's a copy that goes through the mirrored port, and that's where the IDS is. So sniffers are very common. We use a gateway for anything that's, you know, between, like a router we call a gateway, a firewall we can call a gateway. But for this exam, and really what the proper technology or the proper technical definition is that it's working at the application layer. So a real gateway is actually working at an application layer and doing some type of translation between different software that's actually used. So if you see anything that's asking specifically where a gateway works, it's at the application layer, but it kind of confuses people because in the industry we use that term too much. We use it for a lot of different things.
So in this section, we're going to be looking at protocols and then specific attacks on protocols. A protocol is a recipe, if you will, of how a particular type of communications will occur. That's what a protocol is. It's nothing more than a pre-planned mapping of how we're going to communicate, how this dialogue is going to operate. And protocols typically specify a particular port number on the client side and on the server side. Remember, there are two in this dialogue, client and server. So the port number very often identifies what protocol is occurring for that particular frame or transmission. Port numbers are mapped to these specific protocols, and there are many that you should understand. I would know these protocols that are on the diagram before you go take the test. There are many, many others that I would say if you're working in the network engineering arena, you should have memorized off the top of your head. You should know 50 different port numbers and the protocols they map to. However, for the CISSP exam, if you knew these collection of port numbers, you probably have enough to do well on the test. The well-known port numbers live between a range of 0 to 1023. So these are generally server-side port numbers. In other words, the client who is initiating the whether or not the frame makes it to the destination. It's going to give it its best effort to get the frame to the destination. TCP will guarantee that the frame will get to the destination, assuming a connection is possible. So the TCP/IP is a suite of protocols that collectively provide for this transmission of information. I can use TCP for guaranteed or UDP for not guaranteed delivery. And again, I pay the price of higher overhead for the guaranteed delivery. Very much like Federal Express and the US Mail. So TCP, connection oriented. It actually goes through what we call the three-way TCP handshake to establish a session, and then at the end of the session it'll run through a TCP three-way handshake to dismantle the session. It provides error detection and correction. In other words, if a frame does not arrive to the destination in a timely manner, the transmitter will actually retransmit that particular frame. This assures that the recipient is going to receive 100% of the data transmitted. UDP is connectionless. That's User Datagram Protocol. Is connectionless. It is unreliable. In other words, it's a best effort delivery. There is no session establishment. There's no session teardown. Lower overhead. But I don't guarantee that you're ever going to receive the data that I sent. So you might get some of it, you might get all of it, you might get none of it. UDP doesn't care. It just tries its best to get that information transmitted to you. Now the three frames in the three-way handshake is first called the SYN, synchronize. That's from the client to the server. That tells the server, hey server, I want to have a session with you. Synchronize with me my receive window. You synchronize your send window to match the size of my receive window. When the server receives the SYN frame, he understands that the client wants to establish a session, and the client is trying to synchronize the server's send window with the client's receive window. So the server responds back with what's called a SYN-ACK frame. That's the second frame of the three-way handshake. The server says, I acknowledge that you want to establish a session, and you want me to synchronize my send window with the size of your receive window. I acknowledge all that. You need to synchronize, and this is the server talking to the client now. Client, you need to synchronize your send window to match the size of my receive window. And so that's the SYN part of the SYN-ACK. Now, when the client receives the SYN-ACK, the second frame, he then transmits the final frame of the three-way handshake. This is called the ACK frame. The client sends the ACK to the server and says, I acknowledge. We now have a session. I have acknowledged also that I've set my send window to match the size of your receive window. So this is the three-way handshake to build the TCP session at layer 4 of the OSI model. In this diagram, we see some more detailed information about that TCP header. This is where we will identify the flags that say this frame is a SYN frame, or this frame is a SYN-ACK, or this frame is a FIN frame, FIN being final, to tear down the session. So you see the flags section. This is where I toggle on bits that say this is the SYN bit, this is the ACK bit. So that would be the second frame of the three-way handshake. I'm synchronizing with your receive window, and I acknowledge that we have a session being established here. So again, it's in this layer 4 header information where we set these flags to identify what the purpose of this particular frame is. Now that we understand how the three-way handshake works, here's how a bad guy takes advantage of it. What the bad guy does is first he will spoof the IP address of some client, some other IP address that lives on the network where the victim lives. So the attacker picks an IP address of just a user that lives on the same network where the victim is, the server that we're trying to bring down with this denial of service attack. So the attacker builds a frame spoofing the source address of this user that lives on the network, and he sends the server a SYN frame. So the attacker sends the SYN frame to the server. Now the server, of course, is going to respond with a SYN ACK. He thinks he's about to establish a session with not the attacker, but the user that has been spoofed. So the server sends the user a SYN ACK frame. Well, now the user didn't send the SYN frame. This is where the attack comes into play. The user receives the SYN ACK response from the server and doesn't understand what this frame is. So the user simply discards that SYN ACK frame. Meanwhile, the server is holding resources available in anticipation of this session that he thinks is inbound and is a worthy session, something of good use, and his job as a server is to handle these inbound sessions. So the server commits resources to this apparent session that's about to take place. However, the attacker continues to send SYN frames to open up new sessions to the server, yet the server keeps responding back to some other user who doesn't understand what this is all about. He simply discards those frames, but meanwhile the server is consuming more and more and more of his resources for inbound sessions. We send so many SYN frames to the server that we consume all of his inbound buffer space to handle inbound sessions, legitimate sessions. We've consumed all of these resources, and now the server can't handle a legitimate inbound session. This is how we provide this denial of service attack on the server. So again, with the SYN flood, we have the attacker who is sending nothing but SYN frames to the server, which is the victim. Now again, in that SYN frame, he's not using his own IP address as the source address. He's using some spoofed IP address as the source address, so that when the server replies back with the SYN ACK, that SYN ACK frame doesn't actually go back to the victim. That SYN ACK frame doesn't exactly go back to the attacker. It goes to some other spoofed address. The server doesn't really know or care. Now again, the attacker simply sends many, many SYN frames to the server. So many frames that the server will, again, consume resources in anticipation of an inbound session. And we consume so much of his resources for inbound sessions that when the user, which is represented in the bottom of this diagram here, legitimate user attempts to make a session with the server doesn't have any more resources available to honor or support that legitimate inbound session. Again, this is a denial of service attack. This particular one is called the SYN flood. Another attack is called the Teardrop Attack. The Teardrop Attack is another malformed frame type of denial of service attack. What the attacker does is, again, spoofing some other source IP address. He never wants to use his own. He wants to remain anonymous. He'll use a spoofed traverse through this network. An attacker will use this in a bad way to have his frames bypass detecting types of devices, such as an intrusion detection system. So if a bad guy can specify his path through your network, he can avoid firewalls, intrusion detection systems, intrusion protection systems, things along these lines. And this allows him to bypass your security mechanisms. There are two forms of source routing. There's strict source routing, where each hop is specified and the packet has no choices on where it's allowed to go other than the routers that are pre-specified. That's strict source routing. With loose source routing, I can say I need to hit that router there, and a couple hops down I need to go through this other router, and a couple hops after that I need to go through a third router. The in between those 3 points, the packet is allowed to take whatever path it cares to, or actually it's chosen all by the routers, but the routers can forward those packets through other intermediate hops as necessary to get from the first router specified to the second to the third. So that is loose source routing, where some of the routers are specified, but intermediate routers, not each hop is specified. Here we're looking at the different classes of IP addresses. Now this is fundamental. If you're working in network engineering, you need to know these 5 classes of IP addresses, and you need to know the values in the very first octet. This identifies the class of the IP address. The IP address ranges that we're allowed to use for our networks live in the class A, B, and C. Now these would be your standard host or server type of IP addresses. They will be either class A, class B, or class C. I've identified that multicast lives in class D, and remember that ranges from 224 to 239. We talked about this earlier when we looked at Internet Group Management Protocol, IGMP, or multicast. The class E is experimental, and it's reserved for research purposes. It's not usable in your addressing scheme. So class A addresses run from 0.0.0.0 through actually 126.255.255.255. That's a class A, and you notice the important thing to realize here is it's the value in the very first octet that identifies what the class of the IP address is. So the first octet in this case would range from 0 to 126. That identifies this address as coming from originally a class A network. A class B network starts at 128 and ranges to 191. So 128.0.0.0 through 191.255.255.255, this is a class B address. So again, with a class B address, the very first value, the very first octet value, identifies this as a class B. And finally, the class C ranges from 192.0.0.0 to 223.255.255.255. That's a class C IP address. And again, it's the value in the very first octet that identifies this as the class C. Now, the default mask for a class A network is 255.0.0.0. If you understand CIDR notation, that's classless internet domain routing, addressing, CIDR, you'd use a /8 subnet mask. The class B addresses use a 255.255.0.0 subnet mask or a /16. And the class C uses a 255.255.255.0 subnet mask or a /24 subnet mask. The class D, using multicast, doesn't specify a subnet mask other than a /32. This is a single IP address that is this multicast address. So it very often will use a /32 mask. And again, the class E we're not allowed to use for our addressing schemes. IPv6 is the next generation of IP addressing. Currently we're running on IPv4. That's the address scheme that I just described to you. IPv6 is the next generation. IPv4 uses a 32-bit IP address and a 32-bit mask. IPv6 uses a 128-bit IP address and a 128-bit subnet mask. It allows many, many, many more IP addresses, and this is the main purpose of IPv6. We were beginning to run out of IPv4 addresses, and so we had to extend the length of the IP address to increase the number of available addresses. So IPv6 is the upcoming generation of the Internet Protocol. It has many enhanced features because we have learned much more about how to do things. We also have identified many, many more needs that we can satisfy with IP addressing. Those include auto configuration, quality of service, and many other features that will be available when we finally do roll to IPv6. What we're seeing is IPv6 is being much more readily accepted internationally than here in the United States. Here in the United States, we acquired many IPv4 addresses and weren't under quite near the pressure that many international nations, from operating system to operating system, but approximately 12 minutes. In addition to the servers and the clients memorizing MAC addresses for about 12 minutes, switches that operate at layer 2 of the OSI model also memorize all source MAC addresses and which ports that MAC address is connected to. So again, the switch builds this MAC address table and again records source MAC addresses relative to each port. So the switch knows all these addresses. Here in the diagram, what we see is a client that is connecting to a server, and in the middle we have a bad guy named Evil Computer. And what the bad guy is going to do is he is going to poison the Arp caches of the client and the server, so that instead of the frame commuting from client to server, the frame will commute from client to Evil Comp, and then Evil Comp will record it, view it, modify it however he cares to, and forward the frame then from Evil Comp to server. As we see, there are known MAC addresses related to IP addresses for each of the 3 nodes on this network. This is before the Arp poisoning attack. So Evil Comp will now send what's called an unsolicited Arp reply to both the client and the server. Again, typically the way Arp works is client 2 would send out an Arp request that says whoever has the IP address of 10.1.1.10, that's the server, whoever has this IP address, I need your MAC address. The server would then reply, I'm the guy with 10.1.1.10, here's my MAC address, and he would feed that information back to the client. The client would then record that in his Arp cache. Here, where we're using Arp poisoning, Evil Comp is going to send an unsolicited Arp reply to both the client and the server and feed them bad information about the MAC address related to client and server. In this slide, we see the poisoned Arp caches on both client and server. Evil Comp has poisoned the Arp cache on the client side that says if you want to talk to the server, send your frame to the Evil Comp MAC address. And then Evil Comp also tells the server, or poisons his cache and says if you want to send information to the client, you send it to the MAC address for Evil Comp. Next, we're going to talk about Icmp, or Internet Control Message Protocol. Icmp is a protocol that is used on networks, and it was originally intended so that network devices can communicate with other network devices without any human intervention. The point of this was so the network can tune itself. In addition, Icmp is used in a very popular program called Ping. Ping is used to test connectivity from client to server. And when I say client and server here, I'm not talking about the class of an operating system. I'm talking about the client, the guy that initiates the request, and the server, the guy that responds or receives the request. In this particular slide, what we see is the different types and codes related to the different types of Icmp packets. Icmp is used for many different things. As we see, the Icmp type 8 is the echo request used in Ping. That's where a client is testing connectivity to a server. Can I get to you and can you get back to me? That's the Icmp echo request and Icmp echo response or reply. And that would be Icmp type 8. That's the one that most of the time we bump into. There are many other Icmp communications and we see different types there. That's just a sampling of what the Icmp packet types are. Hackers use Icmp to identify or fingerprint an operating system. Different operating systems reply with slightly different responses. So a bad guy will send an Icmp echo request with a particular code, and then depending on how the server replies, the hacker can begin to identify with a great deal of specificity the nature of the operating system that is the victim in this case, that he is fingerprinting. So we first would send an Icmp echo request with a code field not equal to 0. Some operating systems reply one way, Microsoft operating systems reply a different way. Then once we identify this a Microsoft operating system, we send a different Icmp request. and depending on depending on the operating system of the target, they send a slightly different response. Based on these differing responses, I can become very definitive as to what operating system I'm dealing with on the other side. This allows the bad guy then to choose a more likely exploit, something that will be successful on this particular version of operating system. Again, Icmp is used by Icmp is used by an application called Ping. Ping is an application that uses Icmp to test connectivity between two endpoints. Again, the client in this case is the one that is initiating the ping, and then the server is the other end of the connection that will be replying to the ping. So with ping, we use the Icmp echo request. We say to the server, if you can hear me, reply back with this same message. When the frame actually gets received by the server then generates an echo reply to the sender and will place in the payload whatever the message was that was requested in the Icmp echo request. So again, the sender, the client, says, echo this back to me. A particular attack called the ping of death, the sender would say, echo back this 10 gigabyte reply. And the server would then have to generate that 10 gigabyte reply and try and send it back to the client. The problem would be that the client would send so many of these Icmp echo requests with very, very large payloads that the server would consume all of his resources generating and sending out frames to the client to try and respond appropriately to the echo request. The next protocol we're going to look at is Snmp, Simple Network Management Protocol. This is a protocol, uses ports 161 and 162. We talked about ports earlier. And it is a protocol that is used to monitor and manage nodes on the network. You would install an Snmp agent on the clients that you want to monitor. Then there's another piece of software that we would run called the Snmp Management Station. And this is the guy that is going to monitor all the Snmp agents. Recently, SMTP has been supported by SSL. Now we can build an SSL tunnel between client and mail server. Then we can authenticate in this encrypted tunnel, and I can receive all email through the encrypted tunnel. Actually, I can send all email through the encrypted tunnel. Again, authentication was in clear text with SMTP by default. A problem with mail servers is the relay function. Now, when we have a client behind the firewall sending mail through his company's mail server, the client is on the corporate intranet. He's authenticated on the intranet, and he's using his internal company's email server. This is a relatively trusted and secure process. The problem comes when the client is now at a customer's location where he's not behind our corporate firewalls, but he still has to send email. So the client would now connect to the mail server over the internet and then would be able to relay email from the client machine through the corporate mail server out to the recipient, wherever that might be on the internet. This should require strong authentication. Historically, especially in the early days of mail servers, people would set up mail servers and would not authenticate the senders of email through this relay function. We'd call that an open relay mail server. The spammers, of course, love this, and here's why. When a spammer sends hundreds of thousands of pieces of junk mail to clients, they get added to what's called the blacklist. In other words, all mail servers are programmed now. If you see email coming in from this location or from this sender, don't accept it, just throw it in the trash. So spammers get listed on the blacklist, and of course then nobody receives their spam. This is bad news for the bad guys. What they hope to do is find your mail server where relaying has been enabled and is not authenticated, and now they'll send their spam through your mail server and out to all the recipients. What happens is the recipients see all this junk mail coming from your mail server. So now you get added to the blacklist, and now your legitimate email for your corporate business gets rejected by all public email servers. Next, we'll look at a series of protocols First one being FTP, that's File Transfer Protocol, then Trivial FTP, and then we'll look at Telnet. FTP is one of the original sockets-based protocols. It was used to transfer files from one location to another. It uses TCP port 21, also historically used port 20, but these days most of the port 20 information gets tunneled through 21. So these days FTP uses TCP port 21. FTP also requires authentication. The problem with FTP, though, is again, its credentials were sent in clear text in the original protocol. So these days you want to be running FTP through an SSL tunnel or use another secure form of FTP. Otherwise, your usernames and passwords for the FTP clients are transmitted in clear text across the wire. Trivial FTP is another protocol, again, based on FTP, but this is a protocol that does not require authentication. Trivial FTP was used back in the old days when we had diskless workstations where there was no place to store information on the client computers, such as TCP IP address and subnet mask, default gateway, operating system, etc. So a client would boot up the computer. On the network interface card, there was a special EEPROM chip that would hold what's called the boot P, that's the boot protocol information. This was a set of drivers that would get the NIC fired up. It would be a DHCP client, and then it would launch a trivial FTP client service on the client box. This is just barely enough to get the machine awake so that it could now find a TFTP server on the network and download the operating system, which it would load up into RAM, and now we'd have a functional computer. Again, this was in the days of the diskless workstation where there was no place to record any information on the local box. Again, Trivial FTP was FTP with no authentication and was used in the early days of networking. The last one on this list is Telnet. Telnet uses port 23 and was used as a remote configuration tool in the early Unix days. We still use Telnet some today, but at the same time, Telnet also had authentication in clear text. So again, my administrative credentials are sent in clear text over the wire. Real easy for a bad guy to steal this information and then log on and reconfigure all your devices. Some other protocols have to do with the dynamic assignment of IP addresses. The first one we're going to look at is reverse ARP. And you remember ARP is Address Resolution Protocol. ARP translates from IP address to MAC address, layer 3 information to layer 2 information. What reverse ARP does is kind of the opposite. Reverse ARP says, this is my MAC address, can somebody please tell me my IP address? And again, this was back in the days of the diskless workstation where the computer had no place to store the IP configuration. What was known though is the hard-coded MAC address that is hard-coded into the network interface card. So when a box would boot up, it would know its MAC address, but it had no idea what its IP address was. Reverse ARP was the tool that then would go out on the wire, say, this is my MAC address, can somebody please tell me my IP address? And you would have a reverse ARP server on the network. Now, reverse ARP is the grandfather of DHCP. Reverse ARP evolved into the boot protocol, which I had mentioned earlier. And from the boot protocol, we got DHCP, again, with ever more enhancements and additional features and benefits. DHCP is where most of us live today. DHCP is Dynamic Host Configuration Protocol. It is used to dynamically configure the IP information on all of your clients, so that if we had a router fail for some reason and I need all clients to use a different router, I can go change one detail in the DHCP scope and then have everybody refresh their DHCP lease, and suddenly all these clients would be reconfigured automatically with this new default gateway. So again, DHCP uses ports 67 and 68 on the network, and again is used to dynamically configure clients with IP address, subnet mask, default gateway, DNS configuration, WINS configuration, and many other details that are important for the operation of a computer on a given network. These days, DHCP carries many, many more options. These could include domain name. This can include many other details as well.
So now we're going to go through the different types of firewalls, how they work. We'll look at where they should be placed, a little bit about the network architecture that has to do with firewalls. So the first thing is that a firewall needs to be on a lockdown system, and that's what a bastion host is. I've seen in the industry where people actually think that a bastion host equals firewall, but a bastion host actually just means it's locked down, which means all the unnecessary accounts are disabled, unnecessary services and subsystems and administrative tools, they're all not available, they're disabled. Because this is the system that's going to be closest to the untrusted network, the internet, and so it has to be properly locked down. Now even the network administrator tools, some people I see in companies where they'll lock down a system, but the actual tools that they use to administer that system or the systems around it, they won't lock it down. Well, the network administrator tools are very powerful. In fact, most hackers actually use those same tools to hack into systems and take over. So if you don't disable those, you're basically telling the hacker, you don't need to bring your own tools, we got them for you, and you can use them against us. So the firewall software needs to be on a lockdown system. Now, most of the firewalls, like an appliance, means it's a dedicated device, will be on a stripped-down Linux operating system. So the DMZ is a portion of the network where you are going to have systems that absolutely have to be there. The DMZ is you'll have the untrusted network like the internet, then you have your DMZ, which is actually a buffer zone before you get to your internal network. So the goal is that there's more than one layer or device that the attacker has to get through before they get to the internal network. So what goes into the DMZ? Well, only what absolutely has to be in there, because it's going to be more likely under attack if somebody gets through the actual firewall and tries to then attack those systems. It'll be right there. And that's why they have to be very locked down. So in the DMZ, that could be where your web servers are, your external DNS server, external mail server. And so this is just a construct. And we're going to talk about different architectures you can use to set up different types of DMZs. Now, DMZs they can get very complex. And a lot of times in books or in classes, when we go through the actual which we'll talk about, like the screen host or the subnet, they look very simple. But most people who actually do networking and architect networking know that DMZs can be very confusing in that you can have several different systems. You can have systems or different subnets with different addresses. You could have more than one DMZ that has to do communication back and forth. So if the DMZ is not properly configured, and that means the different firewalls, firewall between the internet and the DMZ, and the firewall between the DMZ and the internal network, and those systems that are in the DMZ are not locked down, that's an easy way for attackers to get in. So the different types of firewalls that are out there: packet filtering, application layer proxy, circuit level proxy, stateful firewalls. We're going to look at each one of these, and what you need to know is what layer they work at, what type of protection they actually provide. Now, I said earlier that in the industry, most firewalls aren't this straightforward. A lot of actual firewalls use 2 or 3 of these technologies together. But for the exam, what the exam is going to do is see if you know exactly what the different technologies are. What's a state firewall, what's different from a proxy firewall. So there's been different generations of firewalls, and you need to know the generations. Generation 1 is a packet filtering, which is basically a router with ACLs on it. Generation 2 is proxy, which we'll talk about. Gen 3 is stateful, 4 is dynamic packet filtering, and 5 is kernel proxies. So we're going to go through each one of those, but you may get a question on which generation is packet filtering or something. Now, we actually kind of covered packet filtering when I went through routers, because routers will have ACLs, access control lists, that will make access decisions based on header information. So if you have a packet filtering firewall, it's going to look at the headers in the network, the information in the network header, and a little bit in the transport. So it can make its access decisions, and the network administrator configures based on source and destination IP address, the type of protocols that are used, where it is in the we'll talk about how the handshake, if it's a SYN, SYNAC, ACK, it can make those decisions. And it looks at port numbers. So you could specifically say that any traffic going towards this address, port 80, you'll set up a rule because that'll be your web server. So all traffic will go to that port on that address. So that's why we usually say that a packet filter is a level 3 device. It is a level 3 device, but it also can make access decisions based on the source or the port number, which is actually in the transport header. So packet filtering is the first generation. It doesn't provide a whole bunch of security based on what the other ones we're going to look at. But again, it's usually that first line of defense to get rid of kind of all the garbage that we could easily get rid of. And then the other firewalls are usually behind it that do more processing and dig more into the actual packet itself and making decisions on if this is malicious or if it's allowed or not allowed. Now, the packet filtering firewall, I had said that you can, when you actually make up your ACLs, you'll say from a source IP address, and it could be any, or you could specify a range, or you could specify a specific port address going to wherever the destination is, and the actual ports that the packet's trying to go to. And I said that you can also do filter based on SYN, SYNAC, and ACK. But it doesn't actually keep state, which means it's not going to remember what came before it. So even if you say you allow, in your rule, you allow SYNs and SYNAC and ACK, well, an attacker can actually send a SYNAC. And we go through the actual TCP handshake in this domain. In a TCP connection, there's a SYN packet that's sent over, a SYNAC packet, and then an ACK. So that's the three-way handshake. Now, the packet filter doesn't actually keep track of the SYN, SYNAC, ACK. So it's not what's called stateful. So this actually can be fooled. I could send a SYN-ACK packet over to your system, and what your firewall, if it's packet filtering, it basically is assuming that there's already communication going on because that's the middle of the handshake, SYN, SYN-ACK, ACK. So again, it doesn't provide as much security as the other ones, but very useful, usually like your border routers that will provide this type of security. So since the packet filtering is only looking at headers, it can't detect if the data payload has any type of firewall as a proxy. And what a proxy means, it's a middleman. That's basically the definition of a proxy. It means that you can't talk directly to a system. Like with a packet filter, your packet is going to be inspected, but the packet is actually going to go to the destination on the same circuit. It's not going to be broken up. What a proxy does is it'll take a packet, it'll look for, compare it to the rules, and we're going to talk about two types of proxy, which are application and circuit, and then it'll copy that packet and send it on to the destination. It breaks the connection. That's what a proxy does. It breaks the connection. So let's say you have an internal device that needs to communicate through the internet to some device on my network. So what will happen is your device will send the packet, the proxy firewall will get that packet and make sure that it's legal, make sure it maps to the security policy that's been configured on the firewall. And then it'll make a new identical packet, and then it'll change the header, the IP header, to its address. So proxy firewalls changes the IP header to its own IP address and sends it on. And that allows for nobody to understand or know about your internal IP range and what IP address is. The goal is that the outside only sees this one address. So proxy is a middleman. It breaks the connection, and we're going to talk about two that work very differently. So a circuit level proxy, people aren't as familiar with this terminology based compared to like an application proxy firewall. And it doesn't mean that they're not used. Usually circuit level proxy firewalls are actually built into some type of software. It's built into a firewall that already has some other type of firewall capacity. But what a circuit proxy means is that when a packet comes to the firewall, it will look at the same information as a packet filter. The packet filtering firewall looks at the header information. Remember I said the IP source, IP address, source port, destination IP, destination port, type of protocol, those types of things. So the circuit level proxy looks at the exact same information and makes its decision on where it's going to, if it's going to go or not. But the thing that's different is it breaks the connection. It's actually a proxy. It breaks that connection. So it provides a little bit more security than a packet filter that will just review the packet and let it go. And one type of circuit level proxy that you'll need to know is SOX. SOX is an example of a circuit level proxy, and each one of the nodes, the systems that are going to communicate through that circuit level proxy has to have software. It has to have specific software to be able to communicate to that firewall. We looked at the stateful inspection, which is keeping track of the sessions, and application proxy firewalls, which is getting into how the protocols are being used, how the actual command syntax of every protocol that's coming through. And what's interesting is that, in my opinion, and I may be a pessimist, but we're never really going to get away from attacks. These are always going to happen because if you understand how a lot of the attacks take place and are successful against the network stack, you see that it's very difficult to plan for what's next. What else is the bad guy going to think of? Because in just the network header, there could be what's called a land attack. And the source, that means the source IP and the destination IP are the same address. So it's been manipulated. So the source IP and destination are the same. Well, when the developers wrote the software for this network stack, they never expected a packet to come with the same address because there's no functionality. It doesn't make any sense. So that would be a vulnerability, and some systems would freeze up or they'd reboot. And a lot of the attacks that have taken place, especially the older attacks, has just been flipping bits in like the headers that isn't how it would work. Like for the old attack, it's called an Xmas attack, where all the bits are actually flipped. All the flags are turned on within the TCP header. And in no way would that ever happen. There's no reason for that. So the software was developed not to even deal with that or not to look out for that. And so that's just in the network header. We also have the whole keeping the state of the steps of the protocols. And there's, people come up with different ways of injecting traffic into steps or tunneling through protocols. And so there's a lot of things that it's hard to think of everything that people will do. And then you get higher into the application. And remember, we're talking about a network stack. We're not talking about actually applications. At the application layer, those protocols, there's a lot of attacks that take advantage of those. And it's because that it's very difficult to think outside the box. I mean, developing is difficult enough, and to have all this functionality work, but then to think about all the goofy things that people are going to create and throw at your system, that's why I think that we're always going to have we're going to have some type of attack. But that's why it happens in the network stack, is because the protocols are set up to do communication. That's what these fields and these values are. They're so that one system can understand the other. And when other flags are turned on, they just don't know what to do. They haven't been programmed to understand that, and that's why it's a vulnerability. So the 5th generation is called a kernel proxy firewall. And what that means is, well, there's 2 specific things that make it different. First, the actual packet will go into a kernel. It's not going into software. When you have a firewall and it has to go into the software portion for to be filtered or to be compared to some type of security rules, that takes longer than if it actually takes place in the kernel. And another thing that happens within a filter, or a kernel proxy firewall, is that it will create a virtual network stack for a specific protocol. So let's say that a packet comes in. Let's say it's coming over HTTP, and what the kernel proxy will do is build a network stack with the necessary protocols and the information it's going to look at, and compare it to that proxy. Compare it to that packet. So it's actually going to, based on the packet that's coming, it's going to build a network stack, a virtual network stack, which is basically the virtual rules that each of the headers are supposed to match against, versus the other ones just have like a list of rules. They're not dynamically going to be built based on what's coming over to it. So a lot of the firewalls today have VPN capabilities. It just means that VPN technology has been built into the firewall. VPN allows secure transmission to take place. We'll go over that later in this domain. We'll talk about PPTP, IPsec. But when it comes to the firewall, what the benefit is that when the VPN will actually end, which means that if that data has been encrypted, it'll be decrypted, and then the firewall will apply its security rules right away. Instead of having a VPN device that will decrypt the data and then have to send it to a firewall, it'll go over that line unencrypted. They're actually combined. So what are some of the things that we need to be aware of for firewalls? Well, we should block the Icmp redirect traffic. Icmp is a network protocol that has several different types. Icmp is a protocol used specifically to have error messages and have status information. It's not developed to move user data back and forth. So you would want to block the Icmp redirect traffic, because there's attacks that will actually tell like a router to redirect its traffic to another router. You should not allow source routing, and there'll be an actual rule that you have to write out, like in an ACL, that says don't allow source routing. And what source routing is that the packet actually makes a determination of what hops, what routers it's going to. And you don't want that. You want your routers to control the traffic in your network. So a source routing packet will actually override your network configurations. So you need to make sure that doesn't come through the firewall. disable unused ports and services, disable unused interfaces. You also do not want to allow any packets that are coming in with the same address that you use within your internal network. Why would that be? Well, if you have a packet that's coming in that has the same like one specific address that's in your network range, your IP range, that means that somebody spoofed that packet, because there should be it should be coming from a different network range. So that's a giveaway that somebody's actually spoofed that address. So you want to not allow that. And there's a lot of things that you need to configure and understand, that you want to ensure that broadcast data can't come through, because that could be a denial of service where broadcasts continually come through the firewall into the network. And you want to enable logging. The more logging, the better. And you don't want to use like freeware administration tools, because it's freeware. It's not that they're necessarily bad, but a lot of companies actually use VNC, which is free and allows you to do remote administration, but it could be easily broken. There's a crack for it. I've done it when I was in the information warfare unit. So you have to make sure that your remote administration of the firewall is secure. So we've talked about the different kinds of firewalls. Now, where do we put them? Well, that's the architecture part that we're going to go through. And again, what we're going to talk about is kind of a straightforward, very simplistic types of architectures, and they can get very complex within large organizations. Talk about firewalls, and we'll keep talking about them as though they're just connected to the internet, like we talk about the DMZ and such. But it's important to know that firewalls are used throughout the network to be able to segment different network segments. They should be not just about the internet. Any type of remote access should be going through a route or a firewall. So they're used throughout the network, and they should be. But a lot of the talk that I'm doing, because of what you'll see in the exam, is more about the firewall types and the firewall placements when you're connecting to the actual internet. So we'll look at 4 different types of architectures: packet filtering, screened hosts, dual home firewalls, and screened subnet. So the packet filtering architecture is actually one that's kind of new to CISSP. They had the other 3 for a long time, and now they've added packet filtering, which just means that you have a router with ACLs, and then it goes directly into your internal network. So if you just have a packet filtering architecture, you have a packet filtering firewall, and whatever untrusted network, the internet or traffic's coming through, it's just making decisions based on the header information, and then bam, you're right into your internal network. It doesn't mean that they automatically can get into the other DMZ. So you can have a dual-homed or a multi-homed firewall, which will allow you to build DMZs, basically logical DMZs off that one firewall. Now, a screened subnet is actually creating basically a physical DMZ. You have a firewall, and then your servers, and then a firewall, and then your internal network. So this is one of the most common architecture that's used in the industry, where you'll have a firewall. Now, you may have a screening device before that, but what a screened subnet means is you have firewall, and here is the DMZ. Those are where all the systems need to be bastion hosts, which means they're locked down, and only the systems that have to be there. We talked about like external mail server, external DNS server, your web servers may have to be there. Now, another thing with the screened subnet is some companies, to provide even more security, will ensure that those firewalls aren't from the same vendor. Because if there's an exploit for a firewall, for a firewall product, and I'm a hacker, well, I can get through the first firewall and then I can get right through the second firewall because they have the same software. So some companies use one vendor for one firewall, another vendor for another firewall to make sure that that doesn't happen. Now, when the traffic's coming through in a screen subnet, that first firewall will have kind of looser rules because it's got to allow data to go into the DMZ systems, but then when it goes to that second firewall, they're tighter, meaning that it only allows traffic to go into the internal environment. So the screen subnet actually provides the most security out of the different architects we've talked about. The packet filtering, just one layer. You just have to get through that packet filter firewall. Screened host, you have to get through the screening device, the screened host to get to the internal network. In a screen subnet, you have two firewalls that you have to penetrate before you get into the internal network. So it provides more security, more layers or barriers that the attacker has to get through. Now we're going to look at some dial-up protocols, different types of encapsulation protocols. We'll go into a little bit of data inspection and then look at some VPN technologies. So a dial-up protocol really is just an encapsulation protocol, and it's created so that digital data can go over a telecommunication line. And because a lot of our communications are going over lines that have already been set up for maybe the phone system, or they're specifically laid. So these are encapsulation protocols. Now SLIP was the first dial-up protocol. SLIP was developed when the internet was just mainly mainframes where the different military bases were connected. Some universities were actually connected for research. And what it means is that it's going to put a header and a trailer onto a frame that's going to go over the telecommunication line, because these telecommunication lines weren't developed specifically to move this type of information. So it's actually putting on the header and the trailer so it can be properly interpreted, like at a switching office, and go to the necessary destination. So SLIP is an older protocol. PPP is really its replacement. We don't really see SLIP around anymore. PPP is just the newer, better, stronger SLIP. They both work at the data link layer, and they're both doing the encapsulation of the header and trailer. But PPP has some benefits that we're going to look at over SLIP, but it also allows for authentication. It could do authentication through PAP, CHAP, or EAP, and we'll look at the different types. Now, just because it says a dial-up protocol, it doesn't mean it's just for dial-up. The PPP is used over any type of telecommunication line. So if it's a sonnet ring, or using frame relay or L2TP that we'll talk about, it doesn't mean that you're actually going through a modem. It's just an encapsulation protocol that goes over a telecommunication line. So you'll need to know that PPP works at the data link layer. And remember, we went through all of the layers. You have the application protocols that are going to put its information on. You'll go through the different layers, and each one of those protocols will put their own header and trailer information. And you get down to the data link, and it's the data link layer that knows that this is going over, a sonnet, or it's going to go over UTP, or whatever it's going to go over. This is the one that's more intelligent, and so it will do the framing, which puts the header and trailer on, and then it goes to the physical, which is when it's actually turned into electricity. So why did we have to move from SLIP? Well, SLIP was slow. PPP actually does compression that allows for faster data throughput. It uses sequencing, packet sequencing. It doesn't require an IP address to actually start the connection. And what we mean by that is your ISP, when you connect to the internet, your ISP is going to assign your system an IP address, one of its IP address in a range that it's purchased. But if you think about all of the customers of that ISP, if all of them had static IP addresses, then they'd have a whole bunch of IP addresses that they'd have to pay for. Instead, with PPP, basically I can communicate to my ISP. I could start my authentication process before it actually assigns an IP address to me. So it's allowed to save its IP addresses and use them. Not every single customer has to have an IP address. In SLIP, you had to have an IP address to actually start the connection. With PPP, you start setting up the PPP connection, and then you're assigned your IP address. And PPP has more authentication versus SLIP, which we're going to look at those different types of authentication protocols. Now, one of the authentication protocols is PAP, which is Password Authentication Protocol. It should in no way be used today. It's basically, it should be obsolete. Some actual devices won't have an option for it because all of the data is moved in clear text, including the authentication information. So you have username, password, whatever type of information is going over in clear text, which will allow for sniffing, man-in-the-middle attacks, replay attacks. So that's not secure. That's what we used a long time ago. But as the threats increased, we had to provide more and stronger authentication. Now, CHAP is Challenge Handshake Authentication Protocol. It provides more protection than the one we just talked about, PAP. And how this works is I'm going to log in. I want to connect through my ISP to the internet. I put in my username and password. But what my system software does is sends over just my username over to the authentication server. The authentication server is going to look in its database and
in this next section, we're going to be looking at different protocols. One of them specifically is the multi-protocol label switching, MPLS. This is a relatively new technology, and so we want to give you an introductory level of knowledge on this. Then we'll look at QoS, we'll look at routing and some routing protocols. Two early protocols are SDLC and HDLC. These came to us out of the mainframe era. SDLC was the original, Synchronous Data Link Control Protocol. And this was a polling protocol where the mainframe would poll the dumb terminals. As a user would be entering information into a dumb terminal, the user would be typing. When the user hit the enter button, that would set a flag that says, when you get to me, I've got something to say. The mainframe would be polling all of the clients that are associated or connected to the mainframe, and when it would see this flag turned on, it would download whatever the client had in the buffer, the keyboard buffer. And SDLC was a protocol that helped me do that. The next generation of SDLC was HDLC, High-Level Data Link Control Protocol, and this was a more modern protocol that allowed for greater transmission, greater security, and mainframe to mainframe communications as well. Next, we're going to be talking about MPLS, multi-protocol label switching. Again, a relatively new technology that brings layer 3 functionality, which is a little more sophisticated, a little smarter, but a little slower, to layer 2 in operations. So at layer 2, I'm able to make more intelligent decisions faster than if I were operating without MPLS. So MPLS is where I actually place a prepended header or label at the beginning of a frame that tells the routers, the MPLS routers, how this frame should commute through this routed network, what priority level it has. Sometimes it's very high priority because it's time-sensitive information. Sometimes it's got medium or low priority, not so critical on the time sensitivity. So this is a way for me to pre-program frame by frame with a label right at the very end. It's too large to be managed by a single entity, so it gets broken up into smaller, more manageable components. These are the autonomous systems, and they generally have been assigned to individual corporations or organizations for the maintenance and the administration of those regions of the internet. There are border routers that define the edges, very much like firewalls on our intranet, that define the edge of the autonomous systems. So one company has a collection of networks that they're responsible for on the internet. And there are certain paths into their collection of routers and paths out of their collection of routers and networks. And those are called, these inbound and outbound paths are managed by what are called border routers. Here's a diagram that shows an autonomous system, actually two different autonomous systems that contain different areas or regions. And we have area border routers between these regions, but then also area border routers between the autonomous systems. And collectively, these build the internet. So again, the internet is too large to be managed by one entity or corporation or organization. So what has happened is we've broken it up to divide that administrative and management overhead amongst many different organizations and companies. And the border routers are the devices that connect one autonomous system to another autonomous system, one area to another area. And it's through this building block approach that we're able to get this global giant network that we deal with called the Internet. Now, routing protocols. We have dynamic routing protocols and we have also static routing. Now, static routing is generally used in very small, very stable networks where I might have a routed network with a few routers, maybe 5 or 10 routers, and I will manually configure the route tables on these routers. In other words, I'll teach the router, out of this interface you can get to those 4 networks, out of this interface you can get to those 10 networks, out of a third interface you can get to another 5 different networks. And so I will manually configure the route table on each of these routers. This is called static routing. It doesn't grow with the metric value. So distance vector routing protocols such as RIP and RIP version 2 use a distance vector routing protocol based on the number of hops or the metric between the router and the destination network. A more sophisticated routing protocol is called a link state routing protocol. Now, Ospf, Open Shortest Path First, is a link state routing protocol. A link state routing protocol dynamically makes adjustments. I might know 3 paths to that remote network, and right now this path is my most efficient path. So I'm going to send all frames this way until suddenly this guy becomes a little more efficient. So then I'm going to start sending frames this way. So a link state routing protocol is a little more self-adjusting than a distance vector routing protocol. But because it's self-adjusting, it's a little more intelligent. It has higher resource demands. So I don't want to use a link state routing protocol on a small network. It's not worth the overhead. Distance vector routing protocols were used commonly in smaller networks, up to about 15 hops maximum. Link state routing protocols are used for medium to large scale networks using protocols like Open Shortest Path First, Ospf. We're going to be looking at some of these routing protocols momentarily. And here they are. RIP, the Routing Information Protocol. Again, a distance vector protocol. It was unauthenticated. It was broadcast based. Every 30 seconds, by default, it broadcasts its entire route table on every interface. So this was a very noisy protocol. Again, very weak as far as security was concerned, very subject to attack and compromise. RIP v2 is an improvement to this. It uses authentication. Even though it's kind of rudimentary, it still has authentication. And it also knocked down the broadcast. It now can use multicast or even unicast configurations to knock down some of the chattiness of the protocol. The next one on the list is the Open Shortest Path First, or Ospf. Ospf, as I indicated, is a link state algorithm. Ospf is used for medium to large scale networks, greater than 10 nodes, 10 routers or more, hundreds of routers perhaps. So this guy scales very well, but he's got a great deal of administrative overhead. Ospf uses areas where the routing information communicates very rapidly within the area, and then it has a border router that has a scheduled communication to another area border. Any bad guy could drop a router on a network and just start making announcements about bogus networks. And he would actually poison the route tables of all the routers and can hijack all traffic to his networks where he has sniffers and other sorts of monitoring information. In other words, he can steal all your information. He can denial of service your network by taking legitimate traffic off of your network and misdirecting it to his network. So these were the major types of attacks. In addition, you can also flood a router with too much traffic and cause that router to sometimes fail or at least not be able to accept legitimate packets in that particular port.
So now we're going to go over some MAN technologies, Metropolitan Area Network. And when I was talking about the difference between LAN, MAN, and WAN, it's not just the distance. It's actually the technology that is used at the data link and at the physical layer. So Fddi is a technology, a protocol that's been used over MAN links for quite some time. It uses token passing, which we talked about what token passing is, where token ring is a LAN technology. Fddi actually uses 2 tokens and can work at a higher speed. Now Fddi, that stands for fiber. Now the same technology can actually go over copper, which is CDDI. And the big difference between Fddi and CDDI is the actual length of the segments itself, because photons in fiber can go a lot further than electrons in copper, because the electrons in the copper have, there's more like strain, or it'll do attenuation. So really the big difference between them is how long, or how long you can have your segments. So Fddi has built-in fault tolerance because it has 2 actual networks, so you can think of 2 circles. So this is the primary network, and the data will be going over that. And then if the primary link actually goes down, there's a secondary link that could take over and move the data. So it's built in with this fault tolerance, and it'll happen automatically. But some environments actually use both rings to move data at the same time. So if you do that, then you don't necessarily have that fault tolerance. But they do that because the second line is just there empty, waiting for a failure to happen. Now, a common thing that's used is called sonnet rings, and you may have seen like OC dash a number. That's optical carrier dash, and then that number represents the actual bandwidth that can go over that fiber link. So a sonic ring isn't a technology that works at the data link layer like Fddi, but it is it works at the physical layer because it's going over fiber. But remember earlier I talked about signaling or encoding, because sonnet has a specific signaling. That's what it dictates. It dictates how the data is actually going to move over the fiber link itself. And in sonnet rings, it doesn't matter what type of data that is being moved. And how you could think about it is a sonic ring would actually be like a highway. And a highway can have buses and cars and motorcycles, can have a lot of things that actually go over it. The highway doesn't care. The highway is not going to restrict it. It's the same with sonic rings. You can move voice data, data, video, anything over a sonic ring. So they're used in MANs in metropolitan areas, and then they can be connected to WANs, a WAN link that needs to go farther and maybe connect to another MAN. So they're smaller than WAN, of course, and they'll use a different technology. Basically, if you need to go from a MAN, a metropolitan area network, to another one that's very far away, you'll be going over some type of wide area network technology that we'll talk about. The actual sonic rings connect to each other. Like you'll have, a sonic ring can be like for, let's say, a town, and then all of the hospitals and ISPs and government, everybody connects to the sonic ring. And then you have another sonic ring, and the 2 are connected by a device, of course. And then you'll have another sonic ring maybe for the other town, and then you'll have another sonic ring for the other town. So they all are connected. Now, if you need to just, your packets need to go 2 towns, over, then it's just going to go through these MANs. If it actually has to go across, the world or across a nation or something, it'll go from a MAN to a WAN. And what happens is in a MAN, it will have a head device which will split the type of data it is. So if it's satellite data, the head will actually put it in the format of satellite radio frequencies. If it's wireless, it'll go over that spectrum. If it's voice, it'll go over that telephone network. If it's going over the internet, so at that head, it will determine and put it into the necessary signaling for the different type of data for the different network it's going over.
In this section, we're going to be looking at networking services, specifically domain name services, network address translation, and network information systems. First, we'll look at DNS, or domain name services. DNS is a service that translates friendly names that are intuitive to humans into IP addresses. We don't know the IP address of a particular server, but we do know intuitively the name of the server. So DNS allows us to use the friendly names that are intuitive to humans and will translate that friendly name into the IP address that's required for connectivity in the background. This is all hidden to the end user. It uses a hierarchical naming structure such as www.careeracademy.com. The .com is called the top-level namespace. Career Academy is the second level or tier 2 namespace. That's the specific entity or corporation. And the www represents the specific server or the host name for the server that is the actual target of the request. Again, it translates fully qualified domain names into IP addresses. These addresses and names are recorded in what's called a resource record that gets stored on the DNS server itself. So every computer is a DNS client to DNS servers, typically more than one for fault tolerance. As I indicated, the DNS system uses a hierarchical naming structure. The top of this naming structure is referred to as the root. There is no actual name associated with the root other than root, and it records the locations or the IP addresses for all servers at the top level namespace. So there is a .com server, a .edu server, a .gov server. The root servers, and there are 13 of them on the public internet, the root servers hold the IP addresses for the top level namespace servers like .com, .edu, and .gov. If your query is for www.careeracademy.com, your query would first start at the root. And the root would say, well, he's looking for a .com server, here's a .com server. When your query reaches the .com server, the .com server would hold the IP address of the name servers for Career Academy. You then would be connected to the name server that holds organizations. You will have internal DNS so that on your corporate LAN behind your firewall structure on the intranet, you will be able to identify and locate servers, clients, and services on the corporate intranet. Those are internal DNS servers. In addition, you generally will have public DNS servers as well. These are servers that are available and exposed to the public internet so that public clients can find your web services such as HTTP, SMTP, perhaps even FTP and others. So you will have two different DNS systems. One is publicly exposed and will only hold a few records and be very hardened and very secure. And then we'll have internal DNS to provide internal name and service resolution so that we can function on the corporate network. This is referred to as split DNS. Some attacks on DNS include web spoofing and DNS poisoning. These are two very different things, and students get confused by these. They think one is the other. One leads to the other, and we'll talk about this in just a second. Web spoofing is where a bad guy will actually clone a legitimate website on his server and make it appear exactly like the original legitimate web server. His whole point of doing this is generally to steal private information about the browsers that connect to the website. Then what he has to do That, by the way, was web spoofing. Once he gets this website set up, what he has to do next is he has to attract clients to that bogus website, the spoofed website. And to do that, to get clients to that spoofed website, he will poison the DNS system. This is one of his approaches to attracting clients to his spoofed website. And the way he does this is he will actually poison the DNS server with the incorrect IP address. That is the IP address of his spoofed web server for the legitimate website. In other words, let's say www.careeracademy.com lives at 100.100.100.100 IP address. That's the legitimate website and the legitimate IP address. What the bad guy will do is he will clone the www.careeracademy.com website. He will build in his malicious code, whether he's stealing information, whether he's pumping down malware onto your computers, the browsers that connect up to it. He'll build his malicious content into that website. But then to attract the clients, he will poison DNS and say www.careeracademy.com lives at 200.200.200.200, the IP address of the spoofed web server. So now legitimate clients querying for www.careeracademy.com will be returned from DNS the wrong IP address that will take them to the malicious website. This is DNS poisoning, is the attack on DNS. Web spoofing is the cloning of the legitimate website and the introduction of the malware on that spoofed website. In this diagram, what we see is the attacker would first clone his spoofed website, and we see this at the very top of the diagram. This is the false website with the malicious software installed on it and configured on it to either steal your data or poison your machine with malware. That's his first step. He has to build that spoofed website. Then what he has to do is he has to attract clients to that website. So now he will go attack the DNS server. He'll inject his record into DNS. It says when you're trying to go to the legitimate website, give them the spoofed website's IP address. And now when a legitimate client goes looking for the legitimate website, he gets the IP address of the spoofed web server and will arrive at that spoofed web server unknowingly, might provide his private information, credentials, credit card information, whatever, and or might also be infected with all sorts of malware from that malicious website. So this is actually two different things. First we have web spoofing, that's the cloning of the website with the malware, and then we have DNS poisoning, that's the vehicle that is used to attract the clients to that spoofed website. The next networking service we're going to look at is called NAT, or Network Address Translation. NAT was developed because we were running out of IPv4 addresses, and NAT is a tool that we can use so that substituting private addresses and delivering the frame to the client on the private network. That's the dynamic mapping. And finally, we have port address translation. Port address translation is a subset of NAT. Again, just like I never see a firewall without NAT, I never see NAT without PAT. Port address translation allows one public IP address to be split up by port number and be directed to different internal servers. So let's imagine I only have one public IP address. That would be 100.100.100.100. I could say 100 port 25, send it to this mail server. 100 port 21, send it to my FTP server. 100 port 80, send it to my web server. So I have all inbound frames coming into IP address 100.100.100.100, but depending on the service that the inbound frame is looking for, I can map that to specific internal servers by the use of PAT. So I have static mapping, I have dynamic mapping, and I have port address translation. And here's a diagram of that port address translation. As you see, there is only one public IP address, but as public clients send requests inbound into the NAT server, again, my firewall, they will make those requests to specific port addresses. And my NAT server is then programmed, if you see an inbound frame asking for this port number, send it to this private IP address server, such as 10.0.0.1 in this particular example. Different port number, send it to .2. A third port number, send it to 0.3, etc. So using PAT, I can use one public IP address and support a number of internal services to provide those services to public clients. So PAT is a very useful component of NAT, and almost all servers that run NAT also run PAT, even though they're two discrete protocols. The next networking service we're going to look at is called the Network Information System. This was a way on early Unix systems primarily so that clients could locate services on the network. They refer to the NIS system as the yellow pages, and it was basically a lookup service. A client was looking for a particular service, go look in the yellow pages, and they'll tell you, the yellow pages will tell you where to find that particular service. The early NIS had many vulnerabilities, many failings, and those have been improved with a newer protocol called NIS+, and it improved on security and many other features. Instead of using maps that NIS was originally designed to use, NIS+ uses tables. So tables have replaced the maps in NIS+. There are 17 different types of predefined tables now, and you can add additionals if you had the need to. There's a specific procedure for upgrading from NIS to NIS+, and this is where I would take referrals from NIS clients. I would refer them to the NIS+ tables, and then I can remove the old NIS maps, as we see in the diagram. One of the major benefits of NIS+ is the addition of authentication. In the early NIS days, any client could query the yellow pages or the NIS servers for a mapping of where services are located on the network. What did you just tell the bad guy? You told him where to go find the most vulnerable of systems and services. These days, we want to authenticate every request. I won't answer your question until I know who you are. In addition, I won't add your information to the NIS+ tables unless I know who you are.
So now we'll look at some WAN protocols, and the WAN protocols we use are either packet switching or circuit switching. They're usually packet switching, and we'll look at different protocols that provide that service and what the difference between the two approaches are. Now, circuit switching is really what our telephone network runs over. And it means that it's when I call you, I put in your phone number. What happens is that there's a protocol called SS7, and it's going to go through the switches on this network, and it'll ring your phone to see if you're going to answer or not. But basically, it sets up this link, and all of our voice data will go through those same switches, the same link until we're done. So it builds actually a circuit that's not going to be moving around or going through different switches. It's constant. So a circuit switching environment is the telephone company network. It's called public switch telephone network, or POTS, plain old telephone system, which is not very nice. But this is where that's different than like the internet, and it's different than the WAN links that we're going to talk about. It's providing a constant circuit that all the data that goes back and forth. So what happens like if you're at work, when you make a call, you're going to go through your PBX, which is basically a telephone switch that's on your company's environment. And then it'll go to a central switching office, and that central switching office will have the protocol SS7 that will go and make the actual connection between you and whoever you're calling. Now, it could be a local call, or it could be a long distance call. If it's long distance, then it's got to do a long haul, and it's got to go through more than one station for the sender and receiver. So it's been around for a long time. It's been built up, of course, and we've covered in this domain actually voice over IP. So we're moving away from circuit switching. I don't know if we'll go totally away from it. I doubt it, because it's stable. But this is what we use. This is what's been around, and it's usually mainly for voice data. So even though the circuit communication has been used for quite some time, the actual telephone network has changed from analog to digital. Now, it's not like point-to-point digital. How it works is you have, let's say you're making a phone call. Well, from your phone, your house, it's going to go analog. If something doesn't have anything to communicate and it continually sends over this empty slot, there's something else that's called statistical time division. And what this type of multiplexing does is it keeps statistics on how different devices how much data they send over. So, and it's going to dynamically create that slot based on what was sent before. So, for example, let's say you have a plotter, a printer that's going to send an amazing amount of data. Well, if it only had to go in these time slots, that would take a long time to get the whole graphic or whatever's going to be printed over to the destination. But in statistical time division, the multiplexer can dynamically create how big that time slot is going to be. And it's not going to be like, oh, here comes a whole bunch of data, it better have a really big slot. It's based on statistics of what's happened before, and it'll use that information to determine what type of time slot this type of device actually needs. Now, the frequency division multiplex is different. It's going over spectrum radio signals. And instead of the time division where you have specific blocks cut up, what FDM does is it has a specific spectrum and each signal is working at a different frequency. So you can have one frequency, this is where you move your voice data. Another frequency, this is where you move your data. Another frequency, this is where you move your video data. So frequency time division just means that it's going to go over some type of wireless. You have a spectrum, and each spectrum is assigned to something, either a device or a type of data that is going to go to the destination. So in this situation, computers don't communicate in analog, they communicate in digital. So your digital communication, your digital data is going to be modulated into a signal at a specific frequency, and then it's going to be sent over to the multiplexer at the other end. That multiplexer will then change that analog frequencies into the necessary digital encoding so that those computers can understand it. So circuit switching, I said that we have a specific course. Our voice data is going to go through a specific course, and once it's done, if I call you again, the SS7 protocol can actually set up a different course, but all of our data will continually go through that course until we're done with that call. Now that's different than packet switching, where packet switching is much more dynamic. It could go from one router to another router to another router, and it's based on how busy a router is, the congestion, if a link goes down. So I can actually send you, I can email you, I can send you a document, and my packets could actually take different routes through routers, and then they get to your destination, they have to be reassembled. But this is how the internet was actually developed. The internet was developed to be a redundant communication mechanism for the military. So if one line goes down, there's still another line to be able to communicate. So packet switching is used for like data. Even though we are moving over to voice over IP, what we need to know for circuit switching is that it's a constant circuit that's set up. It's used mainly for voice data. Packet switching is usually data, and it's bursty in nature, and there's specific protocols that we're going to talk about that work in this type of mode. So packet switching is how the internet works, but it's also how different WAN links work. And what that means is a company will actually pay for a WAN link. And we're going to talk about a few different kinds. But the internet, is free. You can move your data, and it can hop from one router to the other based on how congested it is if a link goes down. So it's the internet, but that's different than a WAN link that customers actually pay for. So what we're talking about specifically is what customers will pay for to get a destination like from one office to their other office. So the differences between circuit switching and packet switching that we need to know is that the circuit switching is considered connection oriented because it's going to make that circuit, and all data will go through that circuit until the connection is disabled, until we hang up. The traffic is predictable and constant. Versus in packet switching, traffic is usually bursty, because companies or computers or whatever usually aren't going to send out constant data. They're going to send out bursts of data. So where circuit switching has more of a predictable and constant manner, the packet switching will have bursts of data, and because it's going through all of these different routes, the data can actually show up, the packets can actually show up in different orders, so they have to be reassembled. And that means that the packet switching can have variable delays since they're basically swimming down different streams. So the packet switching mainly carries data. Now we are going over to voice, but for the exam, packet switching mainly carries data, and circuit switching carries voice data. So the two packet switching WAN protocols we'll look at is X.25 and frame relay. Again, this is not the internet. This is something that corporations will pay for to be able to communicate long distances. Now, X.25 was a protocol that came out when the internet first started. And like I said before, the internet really was just a bunch of mainframes that are military institutions and some university institutions. And it used SLIP. We talked about SLIP as a encapsulation protocol over the telecommunication line, and it used X.25, which is it's the packet switching protocol. And so basically you'd have the sender would set up, would pay for this communication line. You'd have the sender and then you'd have the receiver, and X.25 just basically made sure it got to the destination. And it actually did more than just making sure it got to the destination. X.25 is called, it's referred to as like a FAT protocol because it works, we say it's at a data link layer. And that's true, it works at the data link, but it also does some of the network layer stuff. Remember I said that some protocols can actually bleed over because of the amount of functionality they provide. So X.25 actually provides a lot of error checking, a lot of transmission error checking, and it was built FAT because at that time the internet wasn't very stable. So if your topology, if your physical topology is not very stable, then your software protocol has to be, once we're done, those are still going to stay. Those configurations are still going to stay. So the next time one office needs to communicate to the other, it will go over the same setup, the same circuit, which means the same switches. It's not dynamically changed, which is what switch virtual circuit, SVC, is dynamic. The circuit that's set up, the path that's set up is dynamic in nature. So when this office needs to communicate to this office, it will send the data through whatever switches are available. The next time it needs to communicate, it could go through different switches. So PVC sets up a permanent virtual circuit that will always be used between this company. SVC is dynamically setting up, and you could think of it like a phone call. SVC, when I call you, there's a certain circuit that's set up, but then when we hang up, that's broken down, and when I call you again, it may be a totally different circuit. Most companies buy PVCs. SVCs are very rare, so you need to know the difference, but in reality, most of them use PVCs. So the PVCs are the permanent, and SVCs are the dynamic. Both of them, you would actually pay a CIR, the actual bandwidth that you're going to need. So there's one other WAN technology we'll talk about, and it's not circuit switching, it's not packet switching, it's referred to as cell switching. And that's ATM, asynchronous transfer mode. The ATM is much faster than the other two. This is the technology that's used for the core backbones of the internet. Some companies use it, but it's rare because it's so expensive. The service is expensive, the actual hardware is expensive, and most companies don't necessarily need this huge amount of bandwidth that's available to it, but definitely the backbones of the internet do. And the different backbones are maintained by different telecommunication companies, and then those backbones will be connected to other connections, and it'll go down. Basically you have the big dogs, the service providers, and then you'll have the regional ISPs, and then you'll have ISPs underneath that. So the large telecommunications, AT&T and those types will maintain, and you have to pay to be able to use those backbones. So it's called cell switching because it's moving around data that's a fixed size of 53 bytes. And so you think, well, what's the big deal about that? Well, since it's fixed, the actual switching technology and intelligence can happen within the hardware. Packets aren't always the same size. They could vary in size. So packet switching has to happen in software. Anytime something could be done at the hardware level, it's much quicker. So it can move a huge amount of data. It's in these fixed cells, or 53 bytes. You need to know that, and it's the core of the actual internet.
So in this section we're going to be looking at WAN technologies. Dedicated lines like the T1 and the T3, the ISDN, which is a fraction of a T1, DSL, digital subscriber lines, frame relay X.25, SMDS, ATM, and then finally we'll finish up with voice over IP. With dedicated lines, we're talking about wires that are pulled from point A to point B. In other words, there is an unambiguous destination. There's only one place these wires are going to go. They call these point-to-point connections. These are typically like the T1 and the T3. This point-to-point connection is also used in satellite, but of course in the case of satellite we're using radio frequency transmissions over the airwaves. We're not using cabling. In this case we're talking about cabling due to the dedicated lines. So the T1 operates at 1.544 megabits per second and a T3 operates at approximately 45 megabits per second. ISDN, Integrated Services Digital Network, is a subset of a T1. This is a T1 to the connection office for the telco, and then they'd pull an ISDN pair of wires to your home, for example, or your office. This is referred to as the last mile. And this provides slightly higher data rates than a standard analog connection using the old screechy modems, but is relatively inexpensive. It uses circuit switching instead of packet switching. Circuit switching is where when the connection is made, your connection path, the wires between you and the destination, are locked in and you own that connection. You own those wires for as long as your connection is made. Once your connection breaks, those wires are released back and are available for other connections to be made from other clients. But when you call back, you lock in your own connection path again and you don't share that connection path with anyone else. So that is circuit switched. We'll talk about packet switching later on. ISDN is an on-demand service for most users. In other words, we don't dial up and stay dialed up. We dial up only when we need to. This helps reduce the cost. Typically, the ISDN is a fraction or a small component of a T1 connection. It uses typically two B channels, two bearer channels, and a single D channel for the connection. The BRI, or basic rate ISDN, as I indicated, uses two B channels and one D channel to give you 144 kilobits per second. Now, this is two B channels out of the 23 B channels that make up a T1 connection. So the T1 gets broken up into many different ISDN channels, and that T1 can then be shared amongst many different subscribers in the ISDN connection. The next WAN technology we'll look at is called DSL, or digital subscriber lines. DSL is another one of these last mile technologies. DSL is an always-on technology. In other words, when you get connected with DSL, your connection through DSL stays connected 100% of the time. This is a good thing and this is a bad thing. The good news is you don't have the delay in making your connection to the internet to get your email or to get to your favorite website. The bad news is because you're on 24/7, bad guys have 24 hours a day, 7 days a week to break in and exploit your system. So this has led to a great deal of increase in the number of what we call zombies. A zombie is a compromised client computer that is available for the bad guy to perform whatever malicious attacks he cares to do. DSL operates at a high frequency. High frequencies attenuate over distance, and as a result there is a maximum distance that the subscriber can be away from the connection office, the CO, and still receive a worthy signal. The further away from that connection office, the lower the bandwidth for the DSL connection. This is why DSL doesn't necessarily guarantee a high rate of information flow or bandwidth. It is subject to the distance you are physically located away from the CO. There are two flavors of DSL. The first is called asymmetrical or asynchronous digital subscriber line. This is where the connection is optimized for download to the client. This is the way most users use the internet. They upload a few mouse clicks and the tiny couple of bytes for a URL, the web page that they're trying to get to. So very minimal amount of data uploaded, but a great deal of information downloaded. ADSL optimizes for that type of traffic. Lower bandwidth upload, greater bandwidth download. This is asynchronous or asymmetrical DSL. The other flavor is synchronous or symmetrical DSL, and this is where you have the same upload rate as you do download rate. Generally, the two rates will be lower than usual, but they are balanced at least. This means you can provide some services to the internet. In other words, a fair amount of upload as well as a fair amount of download. Another WAN technology is the use of cable modems. Now, cable modems come to us from the cable TV companies. What they realized is they had available bandwidth on their cable TV infrastructure. They spent a lot of money and a lot of effort putting that cable out to 100% of the houses in a particular neighborhood, and if they weren't using the full capacity of the system, they were losing money. They were just wasting money. They figured out they can provide high-speed internet connectivity over the same cable lines as the TV was being propagated over those same cable lines. In the early days of cable modems, anyone on your trunk, and there was a certain connection point that defined your trunk, anybody on your trunk was visible to you in your network neighborhood properties. You could go browse the network and you could see your neighbor's computers. And this was a huge vulnerability in security. These days, that has been eliminated through the use of virtual private networks. Through the use of virtual LANs. And this is where the only two connection points that you are authorized to view when you connect through a cable modem is your computer and the cable company's server on the other end of the connection. So even though all your neighbors are on the same trunk and their traffic is flowing on the same cable wire as your traffic, you are not allowed to see them through the use of this virtual LAN or VLAN. Cable modems are also an always-on technology, which means you are available 24/7 to be hacked and attacked and compromised and have your information stolen, or you become a zombie to a bad guy's distributed denial of service attack. This is where he programs you to typically monitor a internet chat room, and when you see the proper string or code provided in that chat room, which is relatively anonymous, you now will go attack whoever you were programmed to attack. So a bad guy will compromise many, many computers, these are referred to as zombies, and then through the use of anonymous internet chat or the IM, internet messaging, instant messaging, you will then trigger the attack to whatever the victim is that you've been programmed to attack. This diagram shows the trunks that I was describing, and again, in the early days, you would be able to browse all the computers that were on your particular trunk. If your neighbor had a SharePoint and wasn't aware of the fact that he had a SharePoint and wasn't aware of security, you could go peruse your neighbor's hard drive and see what was in his checkbook and all the details. Whatever he had on his computer, you had access to it. Again, these days, the cable companies have secured this through the use of VLANs. The next connection type we're going to look at is similar to wide area networks, but it is a point-to-point technology and communicating with satellites. In other words, I can uplink to a satellite, have the satellite record it, and then distribute it appropriately to the satellite's footprint. That's the area on the ground that the satellite can be seen from. So you would uplink to the satellite to transmit, and then you would downlink to pull information down from the satellite. This, of course, requires sophisticated antenna systems, amplifiers, transmitters, and receivers. Satellite communications can be used in a hybrid fashion. In other words, from the home computer, you use your modem through your ISP to upload information, and typically that information is a mouse click or a few keystrokes of a URL. That gets sent through your slow modem through the ISP out to the internet. But the loop back, the reply back to the user, is propagated through a satellite system that has greater transmission speeds, greater bandwidth. So again, we're optimizing for the typical home user has a very small amount of uploaded information. For that, we'll use the slow, cheap modem. And then the large volume of information that I'd like to get at a faster rate, I'll use the higher performance, higher cost satellite download. As I indicated earlier, depending on the altitude of the satellite and the particular antenna structure of the satellite, those in combination will provide a footprint or the area of coverage on the ground that that satellite can communicate with. That's referred to as its footprint. Today, satellite systems are used in many different forms of communications, whether it's commercial, educational, or even being used by the government. So we have many diverse opportunities to provide internet connectivity through the use of satellite communications.
So this domain, of course, was huge. We've covered an amazing amount of concepts and protocols and technologies. And what now? Well, you have to actually make sure that everything works securely. A lot of the things that we talked about just the functionality of how switches work or how routers work or how specific protocols work. But not only do you need to know the functionality, you need to know the security they provide, the security they don't provide, the countermeasures that need to be put in place, and it could be overwhelming, especially in a large environment, because we're just talking really about the infrastructure, telecommunication and network infrastructure, and then on top of that you have all of your operating systems and your applications, and so the complexity only increases. And security and complexity, they don't get along. Security and simplicity gets along. So this is why as security professionals we could feel safe, we will always have a job. Our environments are unbelievably complex. We have different types of firewalls, IDS, IPS, wireless communication. Pretty soon we're going to have like our smartphones and PDAs authenticating to the network. We have to worry about data leakage and buffer overflows and web server attacks. So security is a place, if you really love to continually learn, that's a place for you. So just realize, again, for the CISSP exam, we're only going 1 inch deep. We're only going 1 inch deep. It's a mile wide, which means we're covering a lot of data, but we're not getting into the depth that you probably really need to know when you're going to practice security. So as we said in access control domain, this infrastructure has to be built in a layered approach. You have to understand how the technology works, and then you have to put the necessary barriers in place so that the bad guy has to go through more than one security device or security software or some type of control before getting to what are you trying to protect. And today it's usually data. Sensitive data is mainly what we're trying to protect.
In this section we're going to look at the telecoms portion of this module. We're going to look at telephony, the traditional telephony components, then we're going to look at voice over IP, and then we're going to consider some of the security issues related to telephony. We're going to look at public switched telephone networks, also referred to as PSTN. This is also referred to as the plain old telephone system, POTS, P-O-T-S. We'll look at data and voice networks and how they operate together and separately. We'll look at analog versus digital systems, and then finally we'll look at the private branch exchange or PBX systems. In PSTN, this is the way we all connect to the telephone systems today. This is an analog line to the house from the CO. At the CO, we are connected to other COs over digital networks, and this is our current technology today for our routine voice over the telephone system. Again, PSTN or POTS, plain old telephone system. PSTN uses a circuit-switched network. In other words, when you pick up the phone and dial grandma to ask for more money, you are actually switched in through a series of switches using pairs of dedicated wires. Those wires are dedicated to your phone call for the duration of that connection. No one else can use those wires while you are using them. But as soon as you hang up, those circuits are released, those wires are now available for someone else to use, and when you dial grandma back, you get switched in using the same or potentially different pairs of wires. In one case, you may go this way to connect to grandma's house, and in another case, you'll connect this way to get to grandma's house over the telephone system. Another aspect of the switched circuit of the telephone system is that every piece of data that gets transmitted will arrive in the voice over IP. Now, voice over IP is a subset of the broader category of IP telephony. IP telephony includes many other technologies. It's a whole family of technologies. Voice over IP is one subset of that. Voice over IP is encoding analog communications, your voice, which is an analog media, if you will, encoding that into digital packets, dropping that onto your IP network, and communicating that information through the IP network to the destination, where that data is then pulled back out of the packet and translated back into analog voice so that the recipient can hear your voice. This was implemented to provide higher quality of service, and it also helps to reduce the cost of long-distance telephone calls. Voice over IP is a packet switch technology. Remember, with PSTN, we had circuit switching where we would switch in specific pairs of wires that would be your connection from sender to recipient. With voice over IP, these IP packets get sent into the cloud of routers between source and destination. Packet 1 might go this way, packet 2 goes that way, packet 3 goes a different way. No two packets aren't necessarily follow the same path. As a result, these packets can arrive at the destination out of order. So they have to be logged with sequence numbers so that the recipient knows how to piece these back in the proper order so that they can play in a continuous data stream. Voice over IP networks experience two serious problems. One is called jitter, the other is called latency. Latency is the delay from the time you speak until it actually gets fully transmitted to the recipient. Jitter is interruptions within that data stream for, let's say, a packet that gets lost in transit. So two different types of problems that go along with voice over IP, jitter and latency. Higher quality systems that include quality of service controls such as Mpls can help to minimize those types of problems. Another side note to remember about voice over IP is that it is currently not regulated by the FCC, since you're not propagating radio frequency information into the airwaves. These days, many companies use a combination of old analog systems as well as the new digital voice over IP systems. Very often, you'll have a mix of these two components together. We'll be looking at IP phones. We'll be looking at PCs that can be turned into telephones themselves, voice servers. We'll then be looking at an IP private branch exchange. We'll look at media gateways. The concept here of gateway is a device that translates from one protocol type to another protocol. So the term gateway means a translation of protocols, and we'll be looking at that more specifically related to voice over IP. And then we'll look at IP and time domain multiplexing, or TDM, trunk lines. So as I indicated, the concept of a gateway is a device that translates from one protocol to a different protocol. And in voice over IP, this is still fairly new technology. There's different manufacturers with different standards and different technologies implemented. And so what we'll need to do for the time being is have a device that will translate between these various different sets of protocols relative to communicating voice data over your IP network. In this diagram, we see the VoIP system on the left and a gateway and gatekeeper towards the center. Now, those gateways, and there, you see them on both sides there, those gateways are there to translate between the analog PSTN and the voice over IP on the private portion of the network. And they also translate between the internet component, or bridge if you will, from gateway to gateway, from the internet portion into the private voice network. Remember, over the internet we'd be using encryption technology as well to secure our transmission data over the internet. So those gateways, in addition to translating the protocols, are probably also VPN servers in addition. Voice over IP, voice over frame relay, and voice over ATM. They all use what's called an isochronous process to reduce delays. And this means they are flagged and serialized as high priority, high quality of service, perhaps using Mpls if the routers support Mpls, and also are flagged as far as how to reassemble them in the proper order. There are many vulnerabilities related to IP telephony. They are subject to all the attacks that our information systems networks are subject to. All of our administrative components must be secured with strong authentication. If the network goes down, of course, our data transmission doesn't happen. There's the reselling of long-distance services. That's a possibility. If someone can connect to your IP network, they can listen in on the phone calls. That's assuming you're not encrypting those IP transmissions. We can always denial of service any of the devices. In other words, just flood the gateways and other devices on the system so that they can't handle legitimate inbound frames. And I also can use these devices as paths into your data network. So if I can dial in and spoof for their own devices. Disable remote access features if they're not required. Disallow local configuration. I think I just said that. Don't let the users configure their own telephones. They'll be loading up software that provide vulnerabilities. It might be Trojaned as well, just because they want to play that latest copy of Whack-A-Mole on their PDA. This is a bad thing. Don't let them do that. And also protect the firmware updating process. In other words, only allow administrators to perform that work. The firmware updating process allows the implementation of malicious microcode into the device. Now, this is at the core of the device, and once it's there, it's almost undetectable. The only way you'll ever get rid of it is if and when you actually do the next firmware update. So don't let the users perform those firmware update processes as well. Here we're looking at the different generations of cellular technology related to information services. First generation, or 1G cellular, provided analog services only for voice transmission. There really was no network at that point in time, and users weren't connecting, even using modems back in those days. 2G, or the second generation cellular, is where we finally introduced the 2400 baud modem or the 300 baud modem. They eventually went up to 56K modems in some cases, but these were still using the analog circuit switch connections and the screechy old modems that you dial up. These were on demand. They weren't always on technology, and this was for low data rates and some voice as well as some low data rates. In addition, we had some basic email, paging, and caller ID services on the 2G. We currently are at about generation 2.5. This is where we have some of the ISDN, the DSL technologies that are always on. This is where I have higher bandwidth capabilities for data. I also do voice over this as well. And I also have the email and paging services that we described earlier. That's currently where we live, about generation 2.5. Our target is 3G, third generation. This is where we have truly integrated voice, telephone type of voice, as well as truly integrated network connectivity. And this is on a roaming scale, a globally roaming scale. This is where we're going. So we have very high bandwidth to the PDA. It's a telephone, and it now is using a circuit switch network, it uses a packet switch network, not the circuit switch network of the earlier 2G. Today's mobile phones use something called the SIM chip. That's the Subscriber Identity Module chip. This is what's used to authenticate your cellular telephone to that particular cellular carrier. So the GSM phones today use these SIM chips for authentication. This is how your number gets programmed in, and this also is your authentication server into your corporate network. The point being here is always, always, always require VPNs between PDA and corporate network. Never let your users connect over the cellular to the wired network on your corporate LAN unless they're running through a VPN first, because again, it could be that 100% of their data is being compromised. So now we'll be moving into a whole new arena. We'll be looking at wireless technologies. This is a new target on the CISSP exam, and there's a great deal of technology to learn and understand relative to securing your wireless networks. We'll also look at instant messaging, another huge vulnerability in your information systems. And then we'll look at some specific attacks on these technologies. The first component that you'll probably acquire for your wireless system would be the access point. The access point is the mediator for the wireless arena or cell. The cell, the definition of a cell, is the wireless access point and all the nodes that are associated to that access point. These wireless technologies are specified by IEEE standards 802.11. That's wireless. There are several others that have been added to this, but the basic wireless standards are based on IEEE's 802.11 standards. Wireless technologies are using spread spectrum technology to provide error-free transmission from sender to receiver. They use access points and then wireless devices. These would be the nodes that are associating with those wireless access points. Some things we'll be looking at are the authentication process, that is, who are you? Okay, I believe you are who you say you are. The authorization process, that says, now that I know who you are you allowed to be touching that? And last one is the association process. Once you are authenticated and I recognize that you are authorized, I will let you be associated to the access point. Association is required before you can transmit your very first data frame. So before you can start using the wireless network, you have to authenticate and be authorized to use the wireless network. We'll look at the wireless protocol stack and some security issues related to the wireless protocol stack and many common attacks on the wireless networks. We'll then also look at how you can defend yourself against these attacks. First, to put it in perspective, what are we talking about here? We're talking about radio frequency transmissions. These are electromagnetic waves that are filling the airspace. They are approximately 4 inches in length for a 2.4 gigahertz system, about 2.5 inches in length for a 5 gigahertz system. These are the two frequency ranges that are allocated for wireless network use. 2.4 gigahertz and 5 gigahertz are the two ranges. Now these are identified in the graphic with the green band and they are about the size of a standard computer mouse. What we see though is that these radio frequencies, these sine waves, can range from the length of a football field or longer, maybe even miles in length, down to so small they are even smaller than the size of the nucleus of an atom. So it's a huge, huge spectrum on the length of these radio frequency waves. We're operating in the range of about 4 inches long for a 2.4 gigahertz system, about 2.5 inches long for a 5 gigahertz system. As I indicated, IEEE wrote a series of standards based on 802.11 that are used to define wireless networking for data communications on your networks. So 802.11 was the first wireless spec. The spec included a speed of about 2 megabits per second maximum. It included 3 different transmission methodologies. The first one was infrared. Infrared really only got you about 1 megabit. And it uses photons, infrared, not visible, photons at 2.4 gigahertz. The second methodology was direct sequence spread spectrum. And the third one was frequency hopping spread spectrum. So this got you up to about 2 megabits per second and operated in the 2.4 gigahertz frequency range. Again, about 4 inches in length in airspace. The second spec that came out was an enhancement or a modification to 802.11. It was called 802.11b. It increased the data rates to 11 megabits per second. Still operated in the 2.4 gigahertz range. Still tolerated all three, infrared, direct sequence, and frequency hopping spread spectrum. And again, increased the data rates to about 11 megabits. The next specification that came out was 802.11a. Now 802.11a was introduced because it operates at 5 gigahertz frequency range. See, the 2.4 gigahertz frequency range is commonly used for industrial, scientific, and medical purposes. And there's a lot of business, a lot of devices operating in the 2.4 to 2.5 gigahertz range. So that meant there was a lot of interference with your wireless networks. So to step away from all that noise, if you will, interference in our wireless networks, they introduced 802.11a. 802.11a operates at 5 gigahertz, which is another section of industrial, scientific, and medical use, but it also includes a range called the Unlicensed National Information Interchange, or the UNI bands. So it gives me a broader spectral range. Here I go from 5 gigahertz to 6 gigahertz, a whole gigahertz of range that I can introduce my information flow on, versus the 2.4 to 2.5 gigahertz. This is only 0.1 gigahertz frequency range. So I have more space, I have fewer devices up there to interfere with, and they also introduced another whole new technology with 802.11a, and that is something called orthogonal frequency division multiplexing, OFDM. Now, OFDM is not a spread spectrum technology, even though it very often gets lumped in that same category. We'll be talking more about OFDM in a few minutes, but you see the data rates here run up to 54 megabits per second. There are also some proprietary technologies that take OFDM up over 100 megabits. So we'll be discussing those in a little while. Now, shortly after 802.11a came out with the introduction of OFDM, the guys in the 2.4 gigahertz range said, hey, if they can do OFDM, we can do OFDM also. And so now they added OFDM to the 2.4 gigahertz range to get the data rates up to 54 megabits. And they operate now with 802.11g at 2.4 gigahertz and 54 megabits. So that's the historical perspective of how we got to where we are with 802.11 and our transmission mechanisms on the wireless networks. Now, 802.11 specified security for the wireless network in a protocol called WEP, Wired Equivalent Privacy. Unfortunately, they had wireless guys, wireless engineers, defining security components. They should have had security guys defining the security components for 802.11. WEP was riddled with flaws. There is vulnerability upon vulnerability in WEP. And once we realized all the vulnerabilities in WEP, they knew they had to fix it. So they introduced another spec, 802.11i. 802.11i is the enhanced security to replace WEP that was introduced in 802.11. It includes two protocols called WPA and WPA2. That's Wi-Fi Protected Access. And the second version of Wi-Fi Protected Access. That's WPA and WPA2. These are solid, secure security for the wireless network, and they solve all the problems that WEP had. If you're running a wireless network, you need to be running 802.11i. We'll be talking more about this in a few minutes. Another spec in the wireless arena now steps away from 802.11. It's 802.15. This is for personal area networks. This specifies networks that range in a wireless fashion up to about 10 meters. That's about 33 feet. This is Bluetooth, Zigbee, infrared. They all live in the 802.11. These all spawn out of layer 2 in the OSI model. So we'll be looking at WEP, we'll be looking at WPA, Wi-Fi Protected Access, and WPA2, Wi-Fi Protected Access version 2. Remember, WEP was introduced in 802.11, riddled with flaws. There's vulnerability upon vulnerability. WPA is the replacement for WEP. And because it uses the same encryption algorithm, its performance hit is about the same as that as WEP. And therefore it's compatible with all the old original 802.11 gear. It uses the same encryption algorithm, RC4, a symmetric key stream cipher, and does not require any more horsepower to do the encryption and decryption than the original WEP required. Now, WPA2 is the eventual only security standard for wireless. They will eventually obsolete WEP and WPA, and everyone will need to be running on WPA2. The difference between WPA and WPA2 is the addition or the change from RC4 used by TKIP as the encryption protocol to using the Advanced Encryption Standard, AES. AES requires a great deal more computational horsepower to do the encryption and decryption. And if we tried to run AES on the old original 802.11 gear, it wasn't strong enough to handle the encryption and decryption in a timely fashion. So what this says is you'll eventually need to throw away all your old original 802.11 gear, and you'll have to buy new gear that will support the WPA2 with the Advanced Encryption Standard. A relatively new technology, 802.11n, has hit the streets in the last year or so. 802.11n increases bandwidth and reliability through the use of multiple transmitters and multiple receivers. The standard is also called MIMO, M-I-M-O, multiple input, multiple output. So I will have an array of transmitters transmitting simultaneously at different frequencies and an array of receivers simultaneously receiving. Now, prior to 802.11n, all wireless transmissions were half duplex. A device could either be transmitting or receiving, but not both at the same time. Whereas 802.11n, because it has multiple transmitters and multiple receivers, can be transmitting and receiving simultaneously. This is called full duplex. This is the same performance we get with our wired Ethernet networks. So 802.11n is a new technology coming about. Again, to a large extent, the technology is leading the standards, but we are starting to see 802.11n devices in the marketplace. As I had indicated earlier, on the corporate network, almost all corporate networks are initialized in the wireless arena with an access point. In other words, I attach a wireless access point to my wired network. This creates a mediator for the cell, and all wireless clients or nodes associate with the access point. And even if a node is talking to another node, the first node will transmit his data to the wireless access point, and the access point will then retransmit the data out to the second node. So there is no node-to-node communications in this infrastructure mode environment. Again, the access point produces what's called the cell. The access point is the moderator for the cell. He controls the data flow. All information flows through him, and he also controls access to the wired network. So he provides a great deal of control in this arena. There are two modes of operation for wireless networks. The first one, as I was describing, is called the infrastructure mode, and that's where I have an access point that is connected to the wired environment, and this infrastructure mode also has this mediator, the access point. In an ad hoc environment, that's the other mode or architecture, there is no access point. And in most cases, there is no connectivity to a wired environment. So it is simply one node transmitting to another node directly, and there's no mediator for the cell. The only thing they have in common is what's called the service set identifier. Otherwise, it's also called a wireless network name. So the service set identifier is how the node identifies what network he's trying to connect to or he is connected to. The SSID, service set identifier, can be any name you care to make it. I believe up to about 32 characters. They are case sensitive. They can include numbers. Basically, this is your network name in the wireless arena. Generally speaking, you want your SSID to be something uninteresting. If you propagate your service set identifier name as Dave's Gold and Silver Exchange, the bad guys are going to come attack you. If you propagate that you are Boeing's access point 211, the bad guys are going to come attack you. You want your service set identifiers to be boring, uninteresting. The service set identifier is transmitted in clear text 10 times a second by default. This is called the beacon. So this is the access point announcing his services as a connection to the wired arena. Again, this is one of those security components that you'll probably want to disable. We'll be talking through the security components of implementing a wireless network. But generally, we'll want to disable the broadcasting of the service set identifier. In addition, you'll definitely want to change it from the default. If you leave your service set identifier set to the default, whatever it was when you bought the access point, once again, you're broadcasting to the bad guy, come get me, I haven't reconfigured this device, and as a result, I might still even be running with the default administrator username and password. You're inviting the bad guys to come attack you if you use a very attractive service set identifier or the default service set identifier. Access points have typically two modes to authenticate users. We have something called shared key authentication, where the access point is configured with a password and the clients are all configured with a password. Or we have open system authentication, where as soon as the client attempts to associate, the access point says, okay, you're authenticated, come on in. Interestingly enough, because of the flaws with WEP, open system authentication is considered more secure than shared key authentication, and we'll talk about why in just a few minutes. So again, two main authentication methods used in 802.11, the original security flaw riddled security 802.11 implementation. They are shared key authentication, the weaker of the two, where we require a password, and then open system authentication, where I don't require a password at all. If you want to associate, you're associated. That's all it takes. Just ask. With 802.11 authentication, again, this is the original 802.11 authentication, not 802.11i. This is before the fix. Again, I had two modes of authentication. Open system did not do any authenticating whatsoever. There's no encryption, there's no challenge, there's no response. Basically, the client says, I'd like to associate with you, access point. The access point would say, you're authenticated, you may associate. Now the client is allowed to transmit his data. With the other type of authentication in 802.11, shared key authentication, a client would say, access point, I'd like to associate. The access point would respond back with some clear text and say, take this clear text, encrypt it with the password, and then send it back to me encrypted. Of course, the access point knows the password. The access point also knows the challenge text, will also do the encryption of the challenge text. And when the client sends back the encrypted challenge text and it equals what the access point knows as the encrypted challenge text, he knows that the client knew the password. The problem is we're showing the bad guy who's watching all this go on. We're showing the bad guy the known plain text and the resulting ciphertext for this authentication process. This gives the bad guy too much information. It makes it too easy for the bad guy to crack the password and now be able to authenticate to the access point. There's a little bit more to this story. We'll talk about that when we get talking about WEP a little further. But again, here, when we use shared key authentication in 802.11, we send plain text challenge text. The client will use the WEP key, which is the shared key. It's a password, if you will. Use the WEP key to encrypt that challenge text and send it back to the client. So a bad guy who's sniffing this transmission is going to see the plain text and the resulting ciphertext. This is called a known plain text attack. It lets the bad guy attack the key and figure out what the key is. Now the bad guy has our key. The problem again with WEP is it's the same key that's used to do encryption of data flow. And this is where the bad guy now can decrypt all of our data that is being used in the cell. So WEP was the security component introduced with 802.11. Again, it was riddled with flaws. We'll be talking about those flaws. Some of the problems that we saw with WEP. First, let's talk about the WEP key. The access point and every client in the cell, that's every client that wants to associate with this access point, uses the same key, the same exact password. This would be like having a corporate network with 1,000 user accounts and all 1,000 users had exactly the same password. What's the point? Anybody can log on using the other guy's password and we'll never know who it really was. In addition, it's this same password used for authentication, the same WEP key used for authentication that is used to encrypt the data flow. So now I'm using this for two purposes. First, if you know the password, you're authenticated. Also, when you do get authenticated and associated, now you're going to use that same password as the encryption key for all data flow. And because of the weakness in the challenge handshake authentication that we saw just a moment ago, if I challenge you for authentication, you see the plain text, the resulting ciphertext, you now can crack the key that authenticates you and decrypts all wireless transmissions for the cell. So WEP had many problems along this line. To take this a step further, there was no way to change or rotate those keys. We all know we should change our passwords on a regular basis. There was no good way to change these WEP keys other than send out an email to everybody and say, please rotate your WEP key, the new password is going to be this. Well, if the bad guy's paying attention, the bad guy is going to catch that transmission and he's just going to roll along with the password change just like everybody else. It required a manual key exchange or rotation, and this was always problematic. Several more vulnerabilities in WEP. As we're doing encryption with WEP, again using the same WEP key, we would add another variable into the equation called an initialization vector, or an IV. Unfortunately, when the guys who wrote WEP implemented WEP, they used an initialization vector that was only 24 bits in length. Now with 24 bits, I have about 16 million different combinations. This means that with every packet I send, I rotate the key, and that says I have 16 million packets that can be sent before I have to start reusing these initialization vectors. When a bad guy records enough information that he sees the reuse of an IV, he now can subtract that as a variable. It's now not variable between those two frames, and the only variable left is the WEP key. So this led to an attack directly upon the WEP key and makes it very easy for a bad guy to crack the WEP keys, now authenticate, associate, and decrypt all data for the cell using the WEP key that is legitimate. Another vulnerability with WEP. WEP uses a symmetric key stream cipher called RC4. Now RC4 is an excellent algorithm. It's an excellent cipher. The problem was it being a stream cipher. Stream ciphers are very difficult to implement properly. And again, I indicated it was the wireless guys, the wireless engineers, that were writing WEP. Well, they weren't cryptographers. You need a cryptographer to write a cryptographic system. And unfortunately, they implemented this RC4 in not the most secure fashion, which introduced additional vulnerabilities in the RC4 process. As I indicated, WEP uses an algorithm called RC4 to do the encryption. RC4 is a symmetric key stream cipher, and it uses a key stream generator. The key stream generator takes inputs that are the key and the initialization vector. The key, of course, is the WEP key, the password that is shared between the clients and the access point. Then the initialization vector is generated from those 24 bits we discussed a little earlier. So the key stream generator uses a pseudo-random number generator combined with the key and the initialization vector to create the key stream. Data, the plain text data that we're encrypting, now gets exclusive ORed with the key stream bit by bit to produce the ciphertext. Yet another weakness with WEP is its weak integrity validation checks. WEP uses a linear CRC function that is directly related to the data, and this is one of the weakest forms of integrity validation. As we implement 802.11i, it solves these problems by using cipher block chaining message authentication code, CBC MAC, and this is a much stronger form of integrity validation. So let's look at a quick list of some of the security issues related with WEP. This isn't a complete list, but this is enough. First, the initialization vector is computational effort required to the same level as what the original WEP was designed to do. So the Wi-Fi protected access, which is part of 802.11i, is designed again for a firmware upgrade to your original old 802.11 hardware. So you would contact the manufacturer, download a firmware upgrade, perform this upgrade on all access points and all clients. This introduces the 802.1x port-based authentication, can use a pre-shared key, which is like a password, can implement many forms of authentication using the Extensible Authentication Protocol, or EAP, and it can also be weakened to the point where we simply authenticate with passwords. It uses an encryption algorithm called TKIP, Temporal Key Integrity Protocol, again based on the RC4 algorithm, but this solves all the problems of key rotation. The problem with WEP was everyone in the cell had the same key for authentication and for encryption. This solves all those problems. It also then uses, instead of the CRC32 hashing function, which is very linear and is closely related to the actual data, it uses an integrity validation check called MICHAEL, or MIC, Message Integrity Code. So again, Wi-Fi protected access, the low end, solves all the security problems with WEP and is considered an acceptable and appropriate step forward if you have 802.11 gear. Now, Wi-Fi protected access, WPA, at some point, and that date hasn't been specified, will be obsoleted, and everyone will need to shift to the WPA2, which is also called the RSN, or Robust Security Network. This is the 802.11i specification in its full glory. We will all need to rotate to this particular standard at some point in time. RSN includes the 802.1x port-based authentication system with pre-shared keys, a password. It uses all the authentication mechanisms that we have with the Extensible Authentication Protocol and can even dumb down to the use of passwords. Here's where it gets heavy. It uses the advanced encryption standard based on the Reindahl algorithm. Now, this encryption algorithm is so strong, so computationally demanding, the 802.11 gear, the old original gear, didn't have the horsepower to run this encryption and decryption in a sufficient amount of time. So this is where you're going to need to replace all of your old gear with new gear so that it has the extra CPU horsepower to run the AES encryption standard. It also then adds to that CCMP, which is CBC MAC for integrity validation, and counter mode protocol for a very sophisticated sequence numbering to make it very difficult for a bad guy to hijack a session. So RSN, which is the equivalent to WPA2, is the high end of 802.11i. It's eventually where we all need to be with wireless security. So 802.1x, port-based authentication. Basically, this allows the client, and in 802.1x specifications, the client is called the supplicant. This is the wireless client that wants to connect to a wireless access point and access the network behind the wireless access point. So the supplicant contacts the access point and requests an association. The access point uses this 802.1x port-based authentication to connect the client only for authentication purposes to the authentication system and does not allow the client to connect to any other services on the wired network other than authentication. So this is where this port-based authentication comes in. In other words, I'll allow the supplicant to communicate with the wired network only for authentication purposes, passing through a radius server that may have its own user database or may contact some other directory service, such as Active Directory for user-based authentication. And only when the radius server approves the supplicant's connection to the LAN will the access point allow the supplicant to forward packets to any other client or network node other than the authentication system. So with 802.1x port-based authentication, again, the supplicant makes the request to make a connection through the wireless access point. The wireless access point is called the authenticator. The authenticator contacts the radius server in the background. It's a separate device, and the radius server submits to the supplicant a digital certificate to authenticate the proper network to the supplicant. In other words, the network is authenticating to the supplicant to prove to the supplicant that he's actually connecting to the right wireless network. This helps to avoid a bogus access point that a bad guy might put up trying to steal usernames and passwords and other information, a man-in-the-middle attack in essence. So again, the Radius server sends the supplicant a digital certificate. The supplicant then uses that digital certificate to build an SSL tunnel for the purposes of authentication. Once the SSL tunnel is established between the supplicant through the access point to the Radius server and the supplicant now begin to negotiate which authentication protocol is common between the two. And they will start with typically the strongest authentication protocol first. The Radius server will ask the supplicant, can you authenticate on this? The supplicant says no. Can you do this? Supplicant says no. Can you do this? Supplicant says yes. This is now the authentication protocol that the two of these will use during this authentication process. The authentication process will continue to the point where the supplicant provides the appropriate credentials, the Radius server validates those credentials, and then approves through the access point the supplicant's connection to the wired network. Another aspect of this is the Radius server can impose many different controls over the nature of the supplicant's use of the wired network. The Radius server can mandate that if the supplicant does not use a proper strength VPN when communicating with the wired network, to disconnect the supplicant. If the supplicant is on the wireless network for too long, disconnect. If the supplicant is using the wrong protocols of any kind, disconnect the supplicant. If the supplicant tries to go to the wrong section of the wired network, disconnect the supplicant. So there are many controls through the Radius system. So 802.1x is not unique to wireless networks. It has just found a very comfortable home in the wireless arena, a very much needed location and utilization in the wireless network. So we see 802.1x port-based authentication used on wireless, token ring, and Ethernet, as well as any other form of networking communications. The authentication mechanisms that we see here are EAP with Cisco Wireless. Now this is called Lightweight Extensible Authentication Protocol. That's LEAP for the acronym. And this requires a Cisco agent on all supplicants, and it requires a Cisco wireless access point. So it's Cisco proprietary. LEAP is a Cisco proprietary authentication mechanism. We have EAP TLS. TLS is transport layer security. This is probably the strongest security at this point in time. This requires digital certificates not just on the network side, on the Radius server side, but also requires digital certificates on the supplicant side. In other words, 100% of your clients connecting to the wireless network would require a digital certificate. This introduces a huge amount of administrative overhead. The next one we see in the diagram is protected EAP. Protected EAP is an authentication mechanism that requires digital certificate on the server side to build the SSL tunnel. This secures the authentication process, but then we can negotiate everything from digital certificate on the client side all the way down to Microsoft's Challenge Handshake Authentication Protocol, a password-based technology for authentication on the client side. This is very convenient and also very secure. We can now implement with a minimum of administrative overhead protected EAP, digital cert on the server side to validate that the client is connected to the right network. This digital cert also is used in building the SSL tunnel between client and server for authentication processes. And then the client can simply use his MSCHAP or MSCHAP version 2 authentication protocol, a password-based authentication protocol. Very easy to implement, very easy for users to utilize as well. And the magic of the extensible authentication protocol is it is extensible. In other words, we can add any new authentication mechanisms and technologies that are developed in the future to the EAP list of usable authentication protocols. So this slide summarizes from weakest to strongest the 802.11 security. 802.11 security uses static WEP. That's where 802.11 security ends. But the fix to 802.11 security and the weaknesses of WEP is 802.11i, which adds to 802.11 dynamic WEP, still fraught with many weaknesses and vulnerabilities, but an improvement over the old static WEP. But then we get to the real full-blown 802.11i using temporal key integrity protocol. Again, based on RC4. Again, it's simply a firmware upgrade for virtually all 802.11 hardware, and it solves all the problems that WEP introduced. So it is a relatively strong security protocol for wireless networking. However, it is temporary. It will be replaced with WPA2 or Robust Security Network, RSN. This uses the AES Advanced Encryption Standard with CBC MAC and counter mode protocol that solves in a very strong fashion all the security issues related to wireless networking. We will all eventually need to get to this WPA2 or RSN that uses the AES with CCMP. So WPA, the low end of 802.11i, uses TKIP, Temporal Key Integrity Protocol, that rotates the keys on a regular basis. Temporal meaning temporary keys that get rotated. Now TKIP uses what's called pairwise master keys. This means this is a pair of keys between a supplicant and the access point, so that a second supplicant has his own pairwise set of keys with the access point separate from the first guy, so that no matter what data is transmitted between supplicant number 1 and the access point, any other supplicant in the cell is not able to decrypt those frames. So I have a specific and discrete pair of keys between the access point and each supplicant. So a different key pair for each supplicant, so that your data frames are now all encrypted securely, strictly between supplicant and access point. There's also a group-wise master key, so that every node in the cell can decrypt the broadcast frames. So the group-wise keys are used for broadcast. Every client in the cell uses the same group-wise key, so that when one guy broadcasts, all the other guys that have the same group-wise key can decrypt that broadcast and understand what the broadcast is about. Again, these keys get rotated on a regular basis using something called broadcast key rotation, or BKR. Again, this is all part of the Temporal Key Integrity Protocol. The RSN, which is the high end of 802.11i, is equivalent to WPA2, and it replaces TKIP with the AES, Advanced Encryption Standard, based on the Reindahl algorithm. Again, it uses CBC MAC with counter mode protocol, and again, it rotates the keys. It also uses the pairwise and the groupwise keys that get rotated on a regular basis. Again, we will all need to eventually rotate to the Robust Security Network, equivalent to WPA2. So here we see the collection of protocols related to wireless and the Extensible Authentication Protocol. It all stems from a point-to-point connection. Wireless is an extension of the PPP protocol. 802.11 is the wireless standards, and they implement 802.1x, port-based authentication, which supports the Extensible Authentication Protocol. And then EAP allows for the addition of any new EAP-compliant authentication mechanism. The list we see here starts with MD5 at the weak end, would use protected EAP and MS Chat v2 at a mid-level. This is equivalent to the tunneled TLS, the TTLS. While we said protected EAP is a Microsoft standard for Microsoft clients, tunneled TLS uses the same type of technology, only it's not vendor specific. So TTLS can be as strong as digital certificates on the client side and as weak as a password type of authentication mechanism on the client side. And it can be used anywhere within that range. PEEP is the same thing, only PEEP is specific to a Microsoft client. Remember, we mentioned lightweight EAP, which is Cisco proprietary. This is the Cisco version of tunneled TLS. And finally, we see the TLS, Transport Layer Security. This requires digital certs on both client and server side, and is the strongest of all based on current technology. So here we see a comparison of EAP TLS with EAP TTLS. And again, the major difference here is EAP TLS requires a digital certificate on both the supplicant side and the Radius server side. The certificate on the Radius server, it performs two tasks. The first task is it authenticates to the client or to the supplicant that the supplicant is attached to the right network. The second thing it does is the use of that digital certificate enables an SSL tunnel that is used for the rest of the authentication process. So all authentication processes now are encrypted in the SSL tunnel. The client-side digital certificate is used to validate the client's identity to the wireless network. Now what happens is once we've got the SSL tunnel built that I described a moment ago, the client submits his digital certificate back to the Radius server. The Radius server compares that digital certificate to the user account database and identifies the proper user account. Based on that user account and the credentials that go along with that user account, the Radius server now will identify, is this the proper client? Is he allowed to access the wireless network? And what are the rules or constraints related to this supplicant's connection to the wireless network? The Radius server then will advise the access point what these rules are. And if and when the client ever violates any of the rules, the access point opens up that 802.1x port and disallows the client connection to the LAN any further. So the EAP TLS uses digital search on both sides, both the Radius server and the supplicant side. And again, this is the strongest form of authentication at this point in time. The problem with this is the greatest amount of administrative overhead. Issuing and maintaining digital certificates on all the supplicants, 100% of the supplicants, is a huge administrative task and will consume a great deal of an administrator's time. An easier and relatively secure substitute for this is EAP TTLS. That's Extensible Authentication Protocol with tunneled transport layer security. What this says is at least a digital certificate on the server side, and I may use digital certificates on the client side, but I may allow as weak an authentication process as passwords on the client side or the supplicant side. So now this affords me a gradient, if you will, of sophistication and security on the client side and allows me to introduce that higher level administrative overhead only where I need the most secure connections. I'll give those guys digital certificates for authentication purposes. And for the masses, where I don't really let them touch anything too sensitive or things along these lines, I'm not too concerned about the information they're accessing, I will still use password-based authentication protocol, much easier from an administrative standpoint, still relatively secure because it's all performed inside the SSL tunnel. And so EAP TTLS is a vendor non-specific digital cert on server side, SSL tunnel for authentication, and maybe as weak as passwords for authentication of the supplicant. Now here we're looking at protected EAP and lightweight EAP. Protected EAP is a Microsoft proprietary technology using MSCHAP and MSCHAP v2 for authentication purposes. Lightweight EAP is a Cisco protocol that your access points and your wireless clients can implement. Always change the default SSID. A default SSID such as Linksys or Belkin or D-Link is a huge red neon sign saying, "Come attack me, I'm an idiot." So always change the default SSID. In addition, you don't want that SSID to be something too attractive. Basically, you want to fade into the background. You want to become shrubbery in this environment. You don't want to be a gold mine, a liquor store, a huge corporation. You want to be something relatively invisible as an SSID. If you can afford to, turn off the SSID broadcast. The access point will by default broadcast the SSID 10 times a second in what's called the SSID broadcast, or it's a beacon. If I turn this off, most lesser sophisticated attackers will not be able to identify your network. However, if a bad guy is determined, there are many, many ways that a bad guy will be able to identify what your SSID is and compromise that information. However, we are putting up layer upon layer upon layer of security. In addition, we're sending a signal to the bad guy that says, I've taken the appropriate steps to secure my wireless network. It's going to be difficult for you to break into my network. There are easier targets. Why don't you move down the street and attack an easier target? So again, as we take these little steps in security, we are telling the bad guy, I'm not going to be an easy target, go someplace else. As part of 802.11i, we should be implementing radius and strong authentication mechanisms. We should be performing cell shaping. Don't propagate your wireless signal 50 yards into the parking lot or 50 yards into the park beside the building. You want to control the shape of your coverage area with your radio frequency waves. In addition, though, let's keep this in mind, with a good Yagi antenna, a bad guy can connect to your access point from 5 or even 10 miles away. So cell shaping is, while it's a weak form of security, it still is one more layer of security in your wireless arena. Always consider your access point and the segments connecting to the access points as hostile. They are as hostile as being connected to the internet directly. So always keep your wireless networks and segments outside of firewall and strongly secure any communications through that firewall to the access points. Treat your access points as hostile. Don't put any other resources on those segments with the access points. If you put a web server on that same segment, it's the same as putting a web server on the public internet without a firewall. Again, treat the access point as hostile as the internet. Always require VPNs for client connections. In other words, I will use SSL to authenticate the client, but once a client is authenticated and the 802.1x switch closes and allows the supplicant or client to connect to the wired network, the first thing we should mandate for that client is that he builds a VPN into the LAN, because again, his frames must commute that wireless segment in clear text unless we build the VPN. So always build a VPN first when your clients connect to the wired network. We have a handful of other controls. We can use MAC address filtering on the clients, but again, a bad guy can defeat this. It's easy to identify approved MAC addresses and then spoof those MAC addresses. There are many tools on the market, relatively easy, and some of them are even free on ways to spoof MAC addresses. We also can require static IP addresses, so now a bad guy also has to guess and spoof the proper IP address to join your network. Again, a bad guy who's sophisticated, this is really no challenge for him. But again, what am I doing? I'm sending the proper signal. I'm not going to be an easy target. Go someplace else. There are easier targets to be had. So 802.11 indicated the security measure of MAC address filtering. This was so that we could build a list of approved MAC addresses on the wireless access point, and only those wireless NICs are allowed to connect to and through the access point. The problem is these MAC addresses are transmitted in clear text in the wireless arena. So all a bad guy has to do is watch or record with a sniffer for a little while to identify a series of MAC addresses that are authorized through the access point, and then using one of the MAC cloning tools or MAC spoofing tools, make his MAC address match the MAC address that has been approved. Now he's bypassed your MAC address filtering. Again though, while this is a thin layer of security, this is still another layer of security. A guy has to be more determined to break into your network because many wireless access points still do not implement MAC address filtering. So as I indicated, a wireless access point, even the early 802.11 wireless access points, included the ability to perform MAC address filtering. Only authorized MAC addresses would be allowed to authenticate and associate with the access point. A bad guy, though, can run a simple sniffer like Ethereal and record approved or communicating MAC addresses. In other words, he'd watch a dialogue and realize this supplicant has an approved MAC address. He would record that MAC address, and then using a tool like we see here, SMAC, I believe this costs $15. There might even be shareware versions of this application on the internet. You can actually modify your own MAC address to match that of an approved MAC address. So again, an unsophisticated attacker might not get past this, but if a guy wants to, if a bad guy wants to get into your wireless network and you're using MAC address filtering, all he has to do is use a free tool like this to spoof that approved MAC address, and he's now passed your security measure. Again though, you're still sending the guy a signal that you are not an easy target and there are easier targets down the road. So a bad guy sniffing wireless traffic can perform something called a wormhole attack. And this is where he runs a sniffer in this wireless arena, records information from you, and then can use a wireless transmitter to send that information bypassing firewalls to an associate that is outside of the corporate environment. In other words, he can use a wireless access point, a rogue access point, to send encrypted information to a bad guy outside in the parking lot. And this data flow is bypassing all of your controls and all of your logging. This is called a wormhole attack. Now, regarding smart cell phones and PDAs, we have another problem. This was discussed a little earlier in this domain. This is called the Wireless Application Protocol. Again, these devices, these portable devices, don't have a great deal of CPU power. They also don't have a great deal of memory. They also don't have a great deal of battery power. So we have to scale everything down to squeeze it into this small portable device. That includes the protocol stack that we use to connect to the wireless network. So all of these components that we use in the wireless devices are a smaller stack and different protocols than what we use on the wired network. As I move data from my portable device through the cellular system, I will be transmitting wirelessly to a cellular antenna that connects to a server. That server is actually going to gateway me to the wired network. So that server now has to decrypt my wireless application protocol stack and then re-encrypt it using the wired protocol stack. So in other words, that server is a gap in the security. 100% of my information will be in plain text on this particular server. We don't know exactly where this server is. We don't know its patch status. We don't know whether or not this server has been compromised. And 100% of my information is in plain text on this server. So this is a huge vulnerability. This needs to be considered in your security policy and security program. And this is again why all wireless communications should first mandate, as soon as a wireless client connects to the corporate network, the first thing they have to do is build a VPN, virtual private network, before they are allowed to touch any network-related resources. Now at least we are running a VPN encrypted data transmission through this gap in the WAP server at the cellular station. So all they see is my VPN encrypted information. They don't see plain text. iMode has the similar problem. iMode is again the internet connections for cellular phones and PDAs, and again it uses an abbreviated protocol stack that has to be translated to a wired protocol stack. And again, the servers that are the connection point between the internet phones and the PDAs must be translated from the short stack to the large stack. In other words, clear text on some server that we don't have any control over. Again, what's the solution? Always require a VPN for communications anytime the information is not public information. Bluetooth is another wireless technology. Bluetooth uses frequency hopping spread spectrum. It operates in the IEEE 802.15 standards. It provides data transfer rates of about 1 to 2 megabits per second. In some cases it can go higher, but these are non-standard. The 802.15 specification says 1 to 2 megabits per second. It works in the frequency range of 2.4 gigahertz. Bluetooth is a huge potential vulnerability in your wireless networking because most people forget that this is actually a wireless transmission. Now the good news is a bad guy has to be within about 10 or 15 meters for most devices to be able to pick up this Bluetooth signal. But remember, I said with a directional antenna, bad guys can be much further away and still pick up a very small signal, such as Bluetooth. When a Bluetooth communication is interfered with, stolen, compromised, whatever, this is referred to as bluejacking. Another huge vulnerability, not related to wireless now, is instant messaging. Instant messaging is used by many people to communicate freely and openly on public instant messaging servers. These are, again, very large vulnerabilities in your corporate network. This traffic should be filtered. There should be security policy that declares this as unacceptable use, and this should all be logged so that we can now either terminate or otherwise punish the employees that are attempting to use this instant messaging in violation of the corporate security policy. This instant messaging traffic is not encrypted, so any information that might be confidential is present in clear text. It is also commonly used to distribute malware. So again, this should be eliminated through the use of administrative security policy. There should be blocks put up on your firewall. There is a process of DNS poisoning that will reroute all the calls to, or all the name resolution requests for these IM servers. We'll simply dump them into the loopback address. So there's many techniques you can use to implement controls to disallow your users from accessing these instant messaging servers. Again, because this information is in plain text, there's eavesdropping problems because this is commonly used to upload and download files. Confidentiality of information can be compromised, and this can be the mechanism, the vehicle that malware is introduced into your corporate network. So again, IM is one of the biggest vulnerabilities that can exist on a corporate network. This should be carefully controlled and monitored. Through the use of firewalls, antivirus software, company security policy, we should control the instant messaging access by your corporate users to these servers. This diagram shows the proper placement for where the instant messaging control should be put in place. This is approximately the same location as a firewall, so these services can be implemented on firewalls. This is the proper place. It should be a choke point. The path from your clients on the left to the internet on the right. This is where these IM servers reside. All of the attempts and even potentially successful connections to these IM servers should be logged for the purposes of prosecution, perhaps, remediation on the clients that are violating your corporate policy, and in some cases, these communications must be recorded for regulatory compliance issues. It can be a violation of the law if you're not recording these communications.
So now we'll do a quick overview of this domain. Telecommunication network security, we've covered a lot. We went through the OSI model. We talked about different cabling and the types of issues that we have with different cabling. We talked about physical topologies, which is different than the data link software protocols that work with the physical topologies. We went through LAN, MAN, and WAN technologies. So LAN would be Ethernet. You could get some questions on token ring. Token ring is basically phased out. It could be in some legacy networks somewhere. So LAN would be Ethernet and token ring. MAN would be Fddi and Sonnet. Then WAN would be X.25, ATM, frame relay. We went through the actual protocols that are used on basically every LAN. We talked about the fault tolerance mechanisms, how certain types of attacks can take place, and again, this is you are working from not only your LAN, but understanding your MAN and potentially your WAN, what security issues can take place through all of them.